Now it's done.
That's better.
I think we can start the adding people in the from the waiting room. Let's say 21.
Yeah. Okay, I'm going to admit all. So Ekaterina, will you take over from here, inviting people and telling them what's happening? Okay, I'm going to go on.
Yes, I can do that. Yes.
Okay, I'm just admitting all. And after that, I'll make Kushagra host. Okay.
All right. Hello, everybody. There is still a few minutes before we start our workshop. Okay, Xian can see us. Can you hear us, Xian?
Hey, I can hear you.
Good. No, Xian cannot hear us. Okay, he can see us, but cannot hear.
Hello, I can hear you.
Okay, nice, thanks.
Margaret, maybe you can share your screen for the talk, just to make sure everything is okay.
Okay, I get a message that says host disabled attendee screen sharing.
Oh, okay. Kushagra, you would have to, I'm no longer host. Could you enable it? And Ekaterina and Xiang, you can also do this. You'll have to go to the participant and enable screen share.
Sorry, to where should we go?
Click on the participant, and I'm no longer able to do it because I transferred. Kushagra, maybe you can do that and tell us exactly what you do. You're on mute, Kushagra. Should you unmute yourself and then?
Yeah, I'm just doing it.
Yeah. It's the first time for all of us.
It's actually all participants who can share. So
you want to do that? That can be disruptive.
Because it's saying that who can share is only host or either all participants.
Let it be all participants then, because we might have a live presentations.
Okay.
So it's then easier.
Okay, for now do that, but we will check that subsequently.
We can
for a small workshop, it's okay, but for a big one, we would have to enable one. So it is possible to enable for an individual.
I think so, yeah. I'll just check it once more. Margaret wants to share?
Okay.
I'll just start with Margaret.
Okay, just a second. Can you
Yes, under.
can you see the screen now?
Not yet.
Okay. Let's go back. Let's try this. Okay, so when I hit the share screen, it comes up with a screen that says desktop, whiteboard, iPhone, a couple of other things. So I pick desktop.
Yeah.
And then it says open system preferences. So I should continue to.
Oh, is it not configured?
Well, I mean, then I go to security and privacy and I clicked Microsoft PowerPoint because that's what I assume, or am I supposed to click something else? Maybe am I supposed to click? No.
So normally when you click on share screen, the
Oh,
default is the desktop and you just have to click on share.
Okay.
If you're going to play any videos, then you have to do a little bit more. Before you click on share, you have to click on share computer sound and optimize.
Right.
screen.
I don't have any videos. I am.
Okay. So then just go back to share screen and click on the share button at the bottom right.
Let's see. Okay, so I am hitting share screen, but it okay, I'm hitting desktop 1.
Yeah, we can see your desktop now. It works.
Can you see it now?
Yep, we can see it.
You can see the slides. Okay, yay. Sorry, this is the first time I've
First time for all of us.
Yeah, done this through Zoom.
And you have 2 more minutes for your talk, so we are in good time.
Okay.
So I may drop out at this point because there's another workshop which I am planning to attend. So it was good meeting all of you. And if there is any issue, Kushagra will help you. And Kushagra, if you have any issues which you're not able to solve, feel free to contact me.
Sure.
Okay, thank you. Have a good workshop.
Thank you.
Meanwhile, I'll request everyone to mute off their mics so that only the speaker can speak at that time. Thank you.
Yeah, thank you.
Okay. So shall we start or?
Yes, maybe we can start.
Yeah, all right. So how many people do we have in this virtual workshop? 46 or?
Yeah, 46.
Yeah. All right, let me start, and then because Gate and I are co-chairing this workshop. So dear colleagues and friends, thank you for participating in this workshop. And please allow me to warmly thank you for participating in the workshop. And also I would like to thank the organizers' effort for organizing this virtual conference and workshop. I understand it is a break of the virus and it takes a lot of effort for doing this issue. So our workshop is focusing on the data engineering for smart cities. Basically, let's focus on different perspectives on the development of the smart cities. For example, we have some publications focusing on integrating the ICT technologies into urban environments. And we have some others, for example, for modeling analytics and optimization for cross-section collaboration and better operational decisions. We have some other research going on for sustainability, wealth, and comfortable support and needs for the people in the community. And we found that the data is a key point for all these topics. So we'd like to focus on the data engineering perspective for smart cities. Regarding to the program today, we have one keynote speaker, which is Professor Margaret Loper. And following that, we have 7 presentations, and we will give the keynote speakers for 1 hour. And following that, we have 7 presentations. Each of these are half an hour. So we are trying to have the intensive schedule. So probably we don't have any break during the workshop, but of course you can get some coffees for yourself. And then let's hope we have some inspiring and successful ideas during the discussions. And I would hope that everybody enjoys the workshop. So Gate will give the short bio for our invited speaker, and so we can start.
Yes, hello everybody. Thank you, Xian. I'm joining the kind words of Xian, and I also would like to thank you all for joining us. And I would like to thank all the organizers. But let's start our intensive program. So we are very lucky today. We have a chief scientist, Margaret Loper, with us. So she's the associate director and chief scientist for the Information and Communications Laboratory at the Georgia Tech Research Institute. So she has been involved in modeling and simulation research for more than 30 years, specifically focused on parallel and distributed systems. Margaret also serves as Associate Director for the Institute for Information Security and Privacy and the Chief Technologist for the GTRI Center of the Development and Application of Internet of Things Technologies. Margaret is currently involved in projects related to smart cities, trust in machine systems, and live virtual and constructive simulation. She holds a PhD in computer science from the Georgia Institute of Technology, MS in computer engineering from the University of Central Florida, and Bachelor of Science in electrical engineering from Clemson University. Welcome, Margaret. We are happy to have you. The stage is yours.
Thank you very much for inviting me to give this talk. So I'm going, oops, let's see.
Can we mute others, or?
Can everybody hear me?
Yes.
Yes.
Okay, good. So I'm going to talk to you today about some work that I have been involved in. It's close to a decade now, related to trust. And so to start that, I think the best way, when I started thinking about how long I've been at some of these different topics, much like you realize that that research is not something that that happens overnight. That oftentimes you start in one direction and your path goes in many directions. So I found this quote that I thought that was quite fitting. From Mish Uvardi, the moral of the tale is that research is a long game. Patience and endurance are necessary components. And so this kind of sets the stage for kind of laying out a lot of this work. And I figured that the best way that to kind of talk about it in context is through timeline. So I'm going to take you back a little bit, many decades, because I want to explain a particular concept to you that'll come up later as we start talking about Internet of Things, smart cities, trust. So I have a long history of research in simulation, specifically in networking simulations together or distributed simulation. And so that work started for me back in around 1990. And with a lot of work in standards creation and something called Lab Virtual Constructive, or LVC. So this is a taxonomy in the simulation world for how people interact with simulations. And so it's best illustrated through this little quad that I have on the right-hand side. So along the x-axis is people, along the y-axis is systems, and then each of those axes is divided into either real or simulated. And it works like this. Real people operating real systems are called live simulations. And so from a public safety perspective, you might think of first responders that are practicing how to use their equipment and how to practice tactics in a lab environment. For example, maybe a building that is going to be demolished, and it's staged as a disaster, and they use that as the backdrop, right? So that could be a live simulation. Real people operating simulated systems is called virtual simulation. And so these are the types of simulation where there's a human in the loop, right? A flight simulator, a car simulator, some aspect where the human is actually operating the system that is simulated. Simulated people operating simulated systems would be illustrated by what in defense world we would call war games or strategy simulations, where everything is modeled within the simulation itself and there's no humans involved other than to set up and run the simulation. And then when this paradigm was created in 1990, the idea of simulated people operating real systems was not fathomed, right? We couldn't really grasp the idea that there would be a simulated person operating a real system. But today we know that that does happen because self-driving vehicles would be an example of that. So I'll come back to this LVC paradigm a couple of times throughout the talk. So just to kind of round it out, I was involved in a lot of work around a particular set of standards called Distributed Interactive Simulation, DIS. We had biannual workshops where it attracted a lot of people, thousands of people every 6 months. We created standards through IEEE, and those standards were very successful. They're still around. DIS is still around today. But DIS really focuses more on that virtual quadrant, right? It was mostly focused on human in the loop types of training simulations. Then in 1996, the recognition that standards are very important. This is a growing area. By the way, all of this work predated, massive multiplayer online games, right? That technology came from this work that was originally done by the Department of Defense. So in 1996, another set of standards were created called the high-level architecture. Their goal was really to support all the live, virtual, and constructive quadrants. So that was why they came about. I personally was more involved in time management services. So this was my dissertation work in how you manage time across all of these different types of live, virtual, and constructive systems. Also a lot of compliance testing, and participated in the standing up a whole standards organization that is an IEEE affiliated group that develops standards. So that's kind of the brief history that tells you, kind of puts in your mind this idea of live, virtual, and constructive. So now we fast forward to 2012. So 8 years or so ago, I started getting very interested in Internet of Things. And so we started to, I started through some internal research at my organization, started to look and see kind of what was our role in IoT. So obviously for this group, I don't really need to tell you what IoT is. This is a particular definition that I like to use from the European Research Cluster on Internet of Things. And so the picture here, the diagram is actually useful in the sense that it starts to call out something that I will also repeat through this talk, is this idea that IoT has different modes of operation, right? It's person to person, machine to machine, person to machine. And so IoT really embraces all of these different modes of operation. So one of the reasons that I got very interested in IoT is the fact that for me, IoT is an LVC system, right? So when all these decades that I've spent in the simulation world, thinking about how people interact with simulations, I started to see the parallels in terms of how people in IoT, people interact with things. So I was able to, to make that kind of jump and say, again, we have people and systems as the axes on this quadrant. Instead of real and simulated, I put real and virtual. But you can see then that we can start to do that mapping, real people operating real systems in terms of live, can be sensors, devices, smartphones, cameras, real people operating virtual systems, mobile apps, social media, navigation systems, virtual people operating virtual systems, the constructive quadrant. So this is a lot of machine learning, analytics, embedded systems, embedded code like embedded simulation. And now we can see that virtual people operating real systems, that autonomy makes sense here, right? In terms of driverless vehicles, robots, or home automation types of systems. So with this recognition that IoT, in my perspective, is just another LVC system, I was trying to get my organization interested in types of IoT research that we could do. And so in 2013, we had an IoT ideation event. And it lasted over 3 days. We had almost 300 people participate in our event, which is about 16% of GTRI employees. And I should have said to start with, GTRI, we are an applied research organization at Georgia Tech. So we are not teaching faculty, we're research faculty. That's our primary role. But out of this event, we generated a lot of comments, almost 1,000 comments around 3 different topic areas: products and services, technology gaps, and what should GT or GTRI's role be. And so you kind of see the breakout there. And so under that role area of comments, we defined different themes where Georgia Tech, GTRI, could actually start to play in the IoT space. It's very obvious from the teaching side of campus, which I refer to here as GT, because of the basic research that is inherent in what faculty do. But GTRI, because we are an applied research organization, there was a little bit more discussion about what our role could be, because we're a university group. We're not going to be able to compete with, Microsoft and Cisco and Google and other industries that partners that are working in this space. And so the themes that came out in terms of areas that we could play are listed here, but the ones that I highlight in red are the ones that we decided made the best sense for us as a starting point. And basically those areas around security and privacy and some testing. So that is we had our narrowed the IoT space to something that was more constrained that we could start taking a look at. And also playing into our decision at that time, the organization I work for, we do work for all kinds of customers, but we do, one of our largest sponsors is military or defense research. And so this quote out of the National Intelligence Council report from 2008 really started to, from a defense perspective, you could start to see why we should be interested in, why my organization should be interested in IoT. And I've bolded the most important, or for this talk, passages, right? That we are unprepared for possible future when internet nodes reside in such everyday things. We don't really understand the future opportunities and risk of when people can remotely control, locate, and monitor everyday things. The fact that IoT could distribute those risks far more widely than the internet has to date. So this kind of re-emphasized the idea that the security privacy aspects of this technology is something that obviously industry and citizens people need to be concerned with. But from a defense and public safety perspective, we also need to be concerned with. So that kind of took us down this idea of really defining kind of our research niche. And so we looked at, we finally settled on this area of security, privacy, and trust. And I found this online many years ago, which I've always thought was a really great way to kind of capture these ideas. And the fact that reliance of IoT on simple, cheap inter-network processors has profound implications on security. The potentially invasive nature of the information gathered has implications on privacy, and the implicit reliance on technology to make decisions on our behalf makes mechanisms for expressing and reasoning about trust essential. So this was at the end of this kind of initial stage of why should we be interested in IoT. This is what we focused on from our perspective. So at GTRI, we have a lab that is focused on cybersecurity. So that was easy to understand how we could contribute in that space. And so then we looked to privacy and trust. And we ended up deciding that we would look down the path of trust first. So that was kind of that was the focus of our work. Kind of in that 2-year time frame, is going through and narrowing down the big space into something that we could really get our hands around and define research projects on. So in the next 2 years, we had some internal funding from my organization to do research in this space. And so trust was the area we were gonna start in. Like any good research, right, you go to the literature and you start seeing who is doing what in the space, what already exists, and you know, how do you even define the area that you're interested in. And so one thing I realized is that a lot has been published on trust, which probably does not surprise anybody on this in this meeting. And there's lots of definitions, right? The competence of an entity to act dependably, securely, and reliably within a specific context. The extent to which one party is willing to depend on somebody or something in a given situation, even though negative consequences are possible. And then we happened upon this definition from NIST, which is a standards organization in the US. And decided that this was really the one that we would settle on in terms of how we thought about trust moving forward. And this comes out of a NIST report on trustworthiness of cyber physical systems. And they define it as the demonstrable likelihood that the system performs according to designed behavior under any set of conditions as evidenced by characteristics including security, privacy, reliability, safety, and resilience. And the reason that I like this definition so much is it really captures the idea that trust is multidimensional, right? And the fact that IoT has these different modes of interaction between humans and machines and machines and machines. That just, the idea then is that there is no one definition of what trust is then in IoT. You have to think about it in all the dimensions that IoT brings forward with respect to these modes of interaction. So about this time, as I was, you know, in this phase of the research, I came across an article out of IEEE Computer Society's Computing Now, and it was a special issue on trust management. And the thing that really attracted me to this article is the idea that they define 2 types of trust in IoT. One that is security oriented, which adopts a restricted view about how, you know, the degree to which an entity is secure. So in this type of trust, You think of it as an absolute property that an entity either has or doesn't have, that it's determined by credentials, that it's enforced in hardware and software behaviors through things like encryption keys, and that you could determine, it could be determined through some formal verification process. The other type of trust is non-security oriented, which then adopts a wider view similar to social sciences. And so in this idea of trust, it is, you think about the mechanism for achieving, maintaining, and reasoning about the quality of service and interactions. That trust is a measurable property that entities have in various degrees. That it is determined on the basis of evidence, like reputation and experience. It's situational, so context matters. And that it includes the notion of malicious and selfish behavior. And so what attracted me to this definition or these, this way of describing trust, the work that's been done in trust, is that it started to really get to that idea that the multidimensionality, right? Where when you're only talking about machines or when you start to include people, that the way you think about trust differs. And so that, based on this, we started some research in specific research projects. And we started with looking at trying to define our trust architecture and what our research strategy was going to be. And so we started with this premise: what if you need to operate in an environment where you don't know if you can trust the sensors, devices, or machines, right? So that's where we started. And I found this other paper in 2014 on trust management for IoT. And it expanded that kind of 2 layers from the previous slide of security and non-security oriented into 3 layers, which capture the physical perception layer. So there's things where the sensors reside and are sensing perceiving the physical and the human environment. A network layer, which we called aggregators in our research. And this is that layer where you transform and process that data that is perceived at the physical layer. And then the application layer, right, where you offer these context-aware services. So think about a command center, command and control environment where humans are now in the loop making decisions. So we settled on this trust architecture, and we started down the path of actually doing research at this point, right? We've a lot of upfront work to really define where we're going, why we're going, and who's done what, and now what are we actually going to do in this space. So I'm going to tell you briefly about some of the research projects that we've done in the trust space over a number of years. And so I'll start with these 3 projects were our first jump into the trust research area. So starting at that network layer where we're transforming and processing perceived data, the first work we did with a professor in College of Computing at Georgia Tech was on machine-to-machine trust. And the idea here was, how do you actually compute trust amongst nodes in an IoT system? And so our scenario or example was self-driving car demonstration, which you see on the far right. And so it was as self-driving cars are moving around an environment, they are exchanging information among themselves and maybe with base stations to communicate information about themselves and their experiences. And so the idea was, is if cars are communicating with themselves or with base stations, how do they trust that between each other, their interactions? And so this work was was a reputation based rating performance system. and was focused on, looked at controlling trust propagation. There's a publication here that you can go read about that research. We did evaluate our algorithm against 5 different attack models, and compared our results to some of the seminal work in the space, Eigentrust being, I think, the seminal work in this area, and showed that our approach actually does have better performance. Also at that kind of middle layer, we did some work in something called Trustmarks, so a trust negotiation language. So there was some ongoing work at GTRI for NIST, for the standards organization, that was really focused on data, enterprise data systems. In it, you know, any kind of enterprise data system. And the basis of this work was to create something called Trustmarks. And these Trustmarks are a formal statement of conformance for some well-scoped set of requirements. And so the way that the original program worked is that you could define these well-scoped requirements. You could have a third party do the assessment, conformance testing, ensure that, you know, you really could provide the service, the resources that you claimed, and you would get a trust mark for that. And that would exist in this enterprise data system. We tried to take that a step further and say, could you make those trust marks computational, where you could actually pass trust marks around among these aggregators, right, in terms of some capability. And so there's an example here. If Samsung created a smartphone with a particular Android capability, Android could grant a trust mark to Samsung, which could be preloaded and presentable on all Samsung-made devices, proving that they adhere to whatever set of requirements that Google defined. Right, so you could do these aggregators trust each other? You could define those areas that they could trust each other in these trust marks. And then at the lowest level, one of the earliest projects we did there was looking at sensor arrays. And so this work came about from some very, very early work that some of these researchers did with Argonne National Labs on the array of things. And they were specifically looking at, our researchers were specifically looking at the security aspects. And so they took that a step further and started to build a few sensor arrays that they could look at privacy preserving algorithms that they could put in these sensor arrays so that you could do that computation in situ instead of sending it back through the cloud. And so this work that they did, they prototyped several of these sensor array boxes. They had 10 different sensors in them and deployed these in Atlanta on something called Atlanta's North Avenue testbed. It's a smart city testbed that the city developed. And so they did a lot of work in terms of what privacy and security by design for these sensor arrays. About the same time, 2 different centers emerged, or groups emerged at Georgia Tech, which were mentioned in my bio. One is our Internet of Things Center called Sedate, which has a number of different working groups and has a lot of different types of industry partners. And they typically meet twice a year and have a number of different types of research projects or efforts going on in these working groups, publishing thought papers and looking at a variety of different topics as specified here around that diagram. And on the right-hand side, the Institute for Information Security and Privacy. This is a group, ISP, that is Georgia Tech wide. So it's not just what I would call the teaching side of campus. It includes not just computing either. It is an organization that branches across the whole Georgia Tech enterprise, including GTRI and our economic development groups, to really bring together the different types of players and researchers around this idea of information security and privacy. And so one of the areas there that ISP looked at was trust, which is how I got involved with that group through this trust research that I've been telling you about. Okay, so that was kind of our first foray into a number of these research projects. And then as we started to gain some experience there on those research projects, what we realized is that, of course, like anything, research is very interesting in itself, but, you know, kind of coming from the GTRI perspective, if there's no real application area that you're focused on, you know, there's a limit to what you can understand about that research. And so we started to shift into not just Internet of Things, trust and Internet of Things, but smart cities. And what does trust mean in that realm? You know, this is a group that I don't have to explain all of these pictures to, but at the time that we were starting to get involved in smart cities, you know, I would go to different expos and conferences, and there's really started to be this emergence of commercial products, smart city products, that were being demonstrated. And you know, this is just a small sampling of those types of products that I would see, but this chart really is to help people who are not as immersed in smart cities as you are, to understand the diversity of products and applications for IoT technology in cities. So from things like smart belly trash cans or smart waste collection, security, so public safety in cities, efficient buildings. I happen to now work in a new smart building, which is having some moderate success. Transportation, which is very easy to understand when we think about our nav applications, but also routing and charging, Wi-Fi kiosk, and then smart street lights. And so with smart street lights, this ties back to the last project I told you about with the sensor arrays, in terms of, you know, using this ground-based infrastructure as a way to deploy technology to look at a variety of things. So during this period of time, Georgia Tech and GTRI had a number of important collaborations around the smart cities community. So I mentioned we had early on done some work with Argonne on Array of Things, really very much limited to the security by design aspects. And we were, like many cities, trying to be an early receiver of AOT nodes. Those researchers then took the work that they were doing in security by design and then took it into the classroom. So Georgia Tech has a program called Vertically Integrated Projects, VIP program, which introduces students as early as their sophomore year to research. So basically, they can take this research program for 3 years and into grad school, where it's basically just a continuing research project. So it's not you do the project every semester. It's the same project. What happens is every semester you build on the previous research that was done to push forward the research projects. And so that happened with some of the sensor research. Then we had collaborations with the City of Atlanta and their smart city initiatives, also with AT&T as they were trying to roll out their initial products, smart city products. And then with NIST and their Global Cities Team Challenge, we were early participants in that. And also Georgia Tech is one of the founding members of the Metro Lab Network Consortium. So we had a lot of stuff going on in this space, and we were really trying to understand, where trusts fit in. So I mentioned earlier that the organization I work for does a lot of defense work. And so one of the things that I also had to help my organization understand is IoT, because one of the things that I continue to hear from many people was that IoT is what, you know, product vendors do. You know, this is what AT&T does, or this is what Google does. This is what Amazon does. It's not what, you know, why would defense be interested in this at all? And so there really actually is a lot of reasons why any country's defense organization should be interested in IoT, as illustrated by the quote that I gave you earlier. But those areas that are well defined and easy to understand are Industry 4.0, so the smart, you know, manufacturing and the Internet of Industrial Internet of Things. Smart bases, right? So bases are just small cities in themselves. And so how does IoT technology help an installation become a more efficient city in itself and protected city? In 2016, the Army Science Board did a study on the benefits and risk of Internet of Things. And then about 5 or 6 years ago, an organization in the US that funds research was interested in this intersection of smart cities, mega cities, and something called gray zones. And gray zones it's a type of warfare that is not kinetic, in the sense that it's not about bombs, it's not about guns, it's about all those other things that present vulnerabilities and risks to cities. And so the perfect example is what we all countries face now, right, in misinformation and influence operations, where people are trying to constantly, through social media, influence you and feed misinformation to, you know, change your opinion. And so that's that general area of gray zone. And so what we learned, right, is that there are many areas that any defense organization should be interested in terms of protecting its citizens. So that kind of took us down a second path of work that we were interested in terms of research. So this is that trust strategy architecture again. And the next set of projects that we did then started to look at the application layer, as well as that physical perception layer. And then something that we did that kind of crosses across all layers. So in terms of the another project that we did at the perception layer was fog computing. And so we had, again, working with faculty on campus that had a fog computing framework. We worked with them to look at fog computing in degraded networking conditions. So what if you don't have reliable network infrastructure that you can connect to? How do you do fog computing in those types of environments? And so our application was pedestrian statistics, worked with some existing data sets that were out that are in the open environment, and to be able to look at security vulnerabilities. So there's some work that's been published on that. Then at the top layer, when we start thinking about where people come into play, some work that we did that started to cross into the more privacy space was this work on privacy zones. And so that the paper that about this work is on the bottom. And so the work here was the fact that location-based services obviously raise concerns over location privacy. You see this in the news all the time now with contact tracing that everybody wants to do with respect to tracking coronavirus. And at the time that we did this work, it was the fact that the permission systems, cloaking techniques are usually rigid, not personalizable, don't have context of where you are, right? So you either have to, it's just all or nothing, and you have to change that manually. And so the privacy zone work was about how to construct more personalized fine-grained regions to protect users' privacy in certain areas under, you know, different spatial, temporal, semantic customization, right? So maybe I want to preserve my privacy when I'm at a hospital or a religious institution, but, you know, I don't care about protecting my privacy if I'm at the grocery store, right? How do you actually do something that is more customizable to meet the needs of people? And then the last project that we did in this space was then thinking about, so we're doing all these individual projects. They're all very interesting. We're learning good things from them. But then the kind of question came up, but how do you know if you can trust a smart city itself, right? So we can tell you, or we can start to unravel the, you know, specific about specific technologies and specific applications, but what about just the city as a whole? And so that was a very interesting question to think about, right? Is how do you think about trust at the composition of all of the things that go into it? And what we realized in this work was that, you know, trust is multidimensional. And you can also think about trust as having an inverse relationship to risk, right? The more risk there is associated with something, the less you tend to trust it, right? And so we wanted to take advantage of that relationship to come up with an idea, these risk factors for assessing, you know, how well a city is doing. So the first risk factor is non-technical. So it's all aspects where humans are involved, right? So this is, you know, where management decisions, training and education, governance, security practice, right? People's willingness to accept technology, all those things that are non-technical sit in one risk factor. Then technical, so all aspects where technology is involved, software development, you know, no software is developed error-free, so there's a, you know, risks that associate there. Devices and data, cyber attacks, and then the last risk factor is complexity, with the realization that a city is a complex, multi-dimensional interconnection of humans and technology. So it's one thing to create maybe these different evaluation factors for looking at non-technical and technical, but then you get to just the complexity of cities themselves. And then when you have the technology there, you run into issues of, you know, having cascade effects or normal accident theory. So this work started to look at how you actually understand what these risk factors are and maybe start to create some type of way to help cities evaluate themselves. And then the one project that we did that I would say kind of cross boundaries was this gray zone modeling, and the idea that the more technology is deployed in a city, the greater the chances, the greater the vulnerabilities are, the more opportunities, the bigger the attack space is in those cities. And so does that create different vulnerabilities for cities with respect to people with malicious intent, right? So if you had somebody who wants to influence people to do something that maybe works against public safety, right? You know, can they use that smart city IoT technology in a way that is malicious to actually, you know, hurt public safety versus, you know, protect citizens? And so we did this work again with faculty on campus. That's a recurring theme here, even though we're a separate organization that focuses on applied research. We frequently do research with tenure track faculty and their grad students. So this was done in collaboration with campus. Okay, so that kind of tells you a lot. And so I just want to wrap up and say, where has this gone and what has happened is I've started to kind of now come full circle and started to think about, so you know, IoT is an LVC system. We started to understand what our niche could be in trust and privacy. We started down this path of doing a lot of different research projects to really understand the space. And then does this now apply to all that research that we did? Does it have any relationship to simulation? And should we even, does it even matter? Does simulation have a role in smart cities? So again, a chart that you don't, I'm preaching to the choir here. So, you know, cities are undergoing revolutionary changes. There are so many different types of places and systems where technology, IoT technology can be used to benefit citizens, to improve services, to make cities more efficient, right? And cities themselves are just undergoing revolutionary changes in the sense that more people are migrating to cities, and therefore having more ways to efficiently run cities to support those their citizens is important. So in 2014, there's a major simulation conference that I go to called the Winter Simulation Conference. And there was a presentation made on kind of the look forward of where simulation was going. And one in this parallel and distributed simulation, past, present, and future, Dr. Fujimoto, one of the M&S challenges that he put out there was using models and simulation to manage the operations of major urban infrastructures, right? That there really is, that as cities are undergoing these revolutionary changes, there is a place for simulation, models and simulation to support that. And one of the areas that he went on to talk a good bit about was something called DODAS, or the Dynamic Data-Driven Application Systems. I can give you links, you can Google it, but I can give links to papers, anybody's interested. But this is what this is if you think back to that LVC paradigm, this is having live data driving constructive simulations mostly, right? Instead of having data that, you know, has been, maybe you're using some statistical input to drive your simulation, or some, you know, data that has been, you know, archived from years ago. How do you actually take live data from real systems to drive your simulations so that they can be faster than real time and do some prediction, some optimization? So that's what Dr. Fujimoto was getting at. And the reality is that their DODAS is being used to monitor, control, and predict cities. So there's examples of it being used for large-scale structural systems. So to predict, understand structural integrity of systems. To look at urban water distribution systems. So monitoring water flow and quality. And then in transportation systems, so doing faster than real-time prediction of traffic in urban areas. So we know that DODAS can be used, so simulations can be used to actually support operating cities. But if the sensors that we are getting that data from, that drive these simulations, are hacked, they could be used for mischief or worse. And so the example being, what if data driving a transportation simulation, so faster than real-time data prediction, made traffic signals stay red or green in all directions. It tweaked electronic speed limit signs, or it sent cars onto the freeway all at once. What if those sensors, you know, how would a city respond to an inadequate supply of electricity or water, or worse, citizens were not notified that drinking water was contaminated, right? What if those sensors had been manipulated? Or what if waste collection was interrupted and garbage piled up in the streets because of the data from the smart trash cans that are used to optimize trash routes was misrepresented, right? So we know that sensors can drive simulations. But are those, can we trust that data coming from sensors to drive the simulation? Because the simulation is going to take for granted what is there, what that data is, and operate it as if it is trustworthy. So then that kind of begged the question, does trust apply to simulations? So we hopefully through this talk I've convinced you that trust is applicable to IoT in all the modes of operation, people to people, machines to machines, people to machines. And IoT is just another LVC system, as discussed before, and therefore does trust apply to simulations? Right, so I would say yes. And I'm going to briefly, as I wrap up, just say, here are the research projects we did, and this is how they might apply to simulations that are going to be used in cities. Okay, so that privacy of sensor data that I talked to you about in both the privacy zones and the privacy security by design and the sensor arrays, right? So that research could apply to the live quadrant of the LVC simulation taxonomy, in that simulations can protect the privacy of sensors, whether it's persons or vehicles that are generating data. In terms of the communication mechanisms at that middle layer, the aggregator layer, both the machine-to-machine trust and the Trustmarks, that research could apply across the board to live, virtual, and constructive simulations. Through helping simulations establish trusted, interactions through reputation ratings and trust marks. The fog computing that we did, that research could apply to live and constructive simulations, in the sense that as simulations are pushed closer to the edge for some type of optimization or real-time prediction, then they need to be trustworthy. Those need to be on trustworthy platforms to have faith in those results. And then from the live, virtual, constructive, and then I would say plus autonomy, that upper right-hand quadrant that was never officially named from the simulation perspective. We could, the work that we did with the Trusting Smart Cities, that risk framework, could be used in the fact that simulations driven by sensors are susceptible to attacks and cascade effects and neural accidents. So that work that we did there could be applied in terms of better understanding how simulations are being used to drive cities. So as I wrap up, I'll just say that I did not actually include the reference on this. I should have. This is another article that was published out of NIST that was looking at IoT trust concerns. So the article was on the technical concerns that negatively affect the ability to trust IoT products and services. And so the top of the slide says a research agenda for simulation ? Right? So is this an area where, if trust applies to simulations and those simulations are used in cities, is this a good set of kind of research areas where, to help us trust simulations that are used in cities? And what I can say is that from a simulation community perspective, there's many of these that we have already done, decades of research on, maybe not related to IoT and not related to smart cities, but definitely things that have to do with synchronization, scalability, heterogeneity, interoperability. We have decades of research in that space that can contribute. But there's other areas that we have never, as a simulation community, really thought about. How does that impact the ability for those simulations to be trustworthy if they're used in systems, in cities? You know, those issues aside, there's also things like insurability and risk measurement that from a simulation perspective, we've never thought about. Maybe since I'm guessing that obviously companies that are developing sensors to deploy in cities do routinely think about that, but that is not something we have thought about from the simulation perspective. So that's it. You know, all these factors represent new areas of research that we can pursue in the simulation world to ensure that simulation trust, you know, that we have simulation trust in untrusted environments. And with that, I think hopefully there's a few minutes left for questions, if anybody has questions for me.
Thank you for the presentation. So let's first ask questions from the audience.
So maybe if somebody has the question, they could just unmute mic, or how do you, Xian, would prefer? Through chat?
There's
In
just one
chat
question
there
from
is
Amma.
A question.
Yeah.
See this
In
domain.
chat, there's one question. Should I unmute him? But I cannot find him.
Okay, so I see that there's a question in chat asking whether this is related to or could be related to autonomous vehicles. So yes, I mean, absolutely. I think that autonomous vehicles, I mean, so I guess there may need to be clarification, but if you're talking about simulation trust, absolutely. When you think about the idea that autonomous vehicles are trained in simulation environments, you know, or in you know, I wouldn't say 100%, but a great deal of training is in simulation environments, and those simulations are of cities and infrastructure being driven by, you know, data collected, you know, from the real world. Then absolutely, I would think that you know, there's a direct relationship there. And just in the sense of, yeah, so I'll leave it at that. I do think that there's a relationship in terms of the work that we've done in trust and IoT, and how that trust work may apply to simulation, and does it have applicability to autonomous vehicles, and how simulations are used to support self-driving vehicles. Yes.
Yes, thank you. Other questions?
Can I ask a question?
Absolutely.
Thank you very much for your presentation. I've just had a lecture with students where we have discussed ethics issues in big data domain. I'm wondering, because in my understanding, ethics and trust are closely related. These are not the same, of course. I would like to hear your opinion or your line of thoughts about that.
You know, I've never been asked that question before. That's that is very interesting. So now you're gonna send me down a path of doing a whole bunch more reading. I mean, I would agree that they are not, that trust and ethics are not the same thing, but I believe that there's a relationship. I don't know that I could clearly articulate that. I have to maybe think about it over the course of the morning and see if I could come up with a better answer. But that's fascinating. Nobody's ever really asked me about ethics before. So yeah, I don't know. I'm stumbling. I don't know how to answer that other than to say I think that there is a relationship, but I couldn't I couldn't, off the top of my head, clearly articulate what that is. Give me a while to think about it, and I'll respond. But I do think that it is. When you think about trust and the trust risk relationship, right? Do we trust things more than we should? Do we trust the simulations? Do we trust the IoT devices more than we really should? Is an interesting question. The ethics of, I wondered, maybe you can expand on the conversation with your students. Ethics seems to get to both a governance perspective, a policy perspective, and a do no harm to people perspective, which you could trust something, you could trust a device, but ethically what that device is doing is not in the best interest of people. And I think that I don't know. I'll think about it. Thanks for asking that.
Yeah, thank you.
I'm sorry. It's like maybe it's too
No,
early.
no worries. There is another question. Thank you for your answer. So there is another question in chat. So are you involved in researching the paired trust of a device and its user and any simulation work in this space?
So I'm not involved in specific research on that right now. Paired trust of a device and its user. Well, I mean, so maybe I'll tell you what I am interested in or looking at right now, which might not be exactly hitting the mark there, but what I'm interested in is the fact that, so during this, our many universities around the world, right, are helping their respective cities or states or countries deal with COVID-19, right? What are the models that you're using? Can you trust the output of those models to make a investment to go build a hospital here, or to deploy resources, right? And so that is something that we're facing in Georgia, in the state that I live in terms of the governor wants to know, okay, the model says that the peak is going to be at this point, then do I need to allocate, millions of dollars worth of funding to go do something to prepare for that? Do you trust the simulation? Do you trust the model that's giving you this answer, right? And so this is a little bit different than the, pairing, trust of a device and its user. But from the simulation perspective, one of the things that struck me is that in these conversations with the state, what they have is they have 5 different models. They have they have a CHIME model, they have a model by a professor at Georgia Tech, they have a model by MIT, they have a model, that's the national IHME model that's being used. So, and all of those models are based on different assumptions and they're giving different answers. How do you trust any of that, right? And because those models are being actually driven by real data that's been collected out of Wuhan or, or New York or wherever. So the data is theoretically trustworthy that you are using to drive those simulations, yet all these simulations are giving you different answers. And so the work that I'm started as recently as last week to help somebody is when instead of trying to connect all those models together, which I've done in a previous lifetime to make them exchange data and work together, can you think about these models like hurricane tracking? At least in the US, we have this sense where there's, 3 or 4 or 5 different hurricane tracking models. And, you run them all with all the data that you have and all the context you have, the trustworthy data. And then you get this kind of cone of uncertainty of where you think that hurricane is going to go and hit landfall, right? And then with each day and more data, you're able to refine and have a more precise understanding. So is there a similar idea in epidemiology, so in coronavirus mapping, right? So what if you do have 5 models? And each of those models is paired with data that's coming from some real world system. How do you get your hands around understanding the risk associated with each model and how much to trust those, so that a user, decision maker, knows when I decide to allocate X millions of dollars to do X, that I know the risk associated with, you know, the model that I'm basing that decision on, right? So how do we start to push that trust up into, so that make it just similar to AI, and how do you make AI more transparent so that people understand how it's making decisions? Is there a similar, you know, paradigm in these simulations where you can expose the risk and the trust to the decision maker? So when they make a decision, they say, I know, you know, it's not that the answer is 42 and I'm going to do it. It's, here's the set of models, here the set of answers. This is the risk associated with each one of those models. And therefore I make a decision accepting the risk that, you know, is associated with this output. Does that make sense? So it's a little bit different than the question that you're asking, but I think that there's some parallels. Okay. So there's my email address. And I'm more than happy if you have any questions for me. If you'd like copies of any of the papers that, you know, or you'd like references to anything, feel free to contact me anytime. I'd be more than happy to provide you with additional information. Or if you have questions that you think of later, as I go think about, just like me, as I go think about this ethics question, then I'd be happy to have a conversation with you about it after the workshop is over.
All right, so let's thank the speaker again. And I think we can start to move on to the presentation from the publications. So the first one is from the presentation will be the Yun Fan Kang, and the title of the paper is the HiDAM, a unified data model for high definition map data. So the stage is yours. I will be unmute her or him. Hello?
Hello, so can you see my screen?
Yes, we can.
Okay, thank you. So good morning. I'm Yun Fan from the University of California, Riverside, and thank you for having us here today. I'm going to present you with our paper, HiDAM, a unified data model for high definition map data. So in this talk, I'm going to first start with a brief introduction and motivation for why we propose this data model. And then I will talk about the data model design briefly. And then I will move on to some our opinions about some discussions on the data model, as well as the high definition map itself. So one of the major components of the smart city is the smart transportation. And one of the hot topics under the smart transportation is the topic of self-driving cars. And self-driving cars has several advantages, such as it can reduce emission and may increase the road safety. And by deploying more and more self-driving cars on road, we can also reduce the amount of traffic on the road. However, the existing map platforms may not be suitable for the self-driving cars because those map platforms are deployed, built, and designed with the assumption that a human user will be consuming the map data from a computing device such as our phones. And we call this map platforms to be designed for human-to-machine interactions. However, over the past few years, the rise of self-driving cars technology has triggered an urgent need for a new type of mapping data that is designed, built, and deployed for machine-to-machine interactions because in those applications, such as the self-driving cars, the human driver is now being replaced with an automated machine driver. And this is also the main motivation behind the high definition maps. So the high definition map will contain more accurate and detailed centimeter level 3D information, and it can serve several new applications. For example, for autonomous vehicles, it can facilitate the applications such as self-localization and risk and obstacle avoidance. And it can also, the map can store prior information for real-time computations. For example, if a self-driving car wants to determine what's the status of a traffic light, it can actually use the pre-stored information about where the traffic light is to save its computational power when doing, for example, image recognition. And the high definition map can also enrich the driving experience for human drivers. For example, it can improve the user experience for advanced driver assistance systems or others. And it can also enable the applications for lane level navigation because it contains more detailed lane level information. But we also have observed that the existing HD map data formats may not be suitable, because on one hand, the commercial HD map models are confidential, and we also observe some complaints from the researchers that they are too complicated, and also the features they support may not be suitable for researchers. And those researchers who have those kind of concerns tend to design their own data models, but also different data models used in different research works may downgrade the reusability of the data and also hinder the experiment that need to be performed on different data sources because they're in different formats. So the goal for designing the HiDAM, which is our data model for the high definition data, is there are three major goals. The first one is to design a research-friendly standard for HDMap data. And the second one is to maintain a widely used node and edge model, because we want to maintain the capability of our model to serve the existing applications. And the last goal is to adapt the information about all the objects in outdoor space so that we can serve more new emerging applications such as self-localization for the self-driving cars. Here's a high-level overview for our data model. It contains two major parts. The first one is the landmarks, and the second part is the road network. And we are going to start with the road network. So we're first going to describe the definition for the lane and lane bundle, and then we will talk about the how we use the definition of lane and lane bundle to compose and enrich the traditional intersection and edge model. So the lanes are they correspond to the driving lanes, are modeled as 3D surfaces. For example, there's an example of the lane here. So each lane will start and end with a cross-sectional boundary, and those cross-sectional boundaries will connect two lanes from two different lane bundles. Each lane will be associated with a lane reference geometry to show the orientation of the lane, as well as locate the point attributes and the range attributes associated with the lane. An example for a point attribute can be like a vehicle checking point. So at this point, a place can stop a vehicle to do some checking for legitimate reasons. And the range attribute could be a speed limit. For example, in this range of this lane, and the speed limit is 30 miles, while in other parts of the lane is 40 miles per hour. So the lane bundle will be defined as a group of parallel lanes in the same road segment. And a lane bundle reference is also associated with each lane bundle to record the attribute of the lane bundle. And those attributes will be applied to all the lanes within the current lane bundle. And the lane bundle also starts and ends with a cross-sectional boundary, which is represented by a polyline that is the union of all cross-sectional boundary lines of all the lanes within the lane bundle. So with the definition of the lane and lane bundle, we try to extend the traditional edge and intersection model. So an edge, which is a road segment, is composed by one or more connected lane bundles. For the intersections, which is in the blue rectangle here, it is a group of overlapping lane bundles in different directions based on the type of intersections. And each lane bundle in the intersection connects two lane bundles that belongs to two different road segments. For example, this lane bundle will connect this lane bundle and this lane bundle here, and this lane bundle in the intersection will connect those two lane bundles that are in the same direction. So next, we will move on to talk about our definition for the landmarks. And the landmarks will have two subclasses. They are the on-road landmark and outdoor landmark. So we define landmark to include all the objects in the driving environment, and the on-road landmarks refers to the landmarks that are associated with either the road segment or the intersection, and they are considered to be part of the driving road. So the examples for the on-road landmarks could be landmarks and traffic lights, road signs, and guardrails. So those on-road landmarks will carry certain attributes or will lead to the change of attributes of lanes or lane bundles on certain directions. For example, we can determine whether we can make a U-turn or just change lanes to bypass another vehicle by looking at the landmarks that separate two lanes in the same lane bundle. And when we determine whether we can just proceed to the intersection, we will rely on the status of the traffic light. So the other group of the landmarks are the outdoor landmark. And we want this group to contain other real objects that exist in the outdoor space, but they are not part of the road network. The examples for the outdoor landmark could be the buildings, trees, parking lots, lights, and parks. These objects are they are diverse and they are of different natures, could have different usages for HD map consumers. For example, the trees and lights along the road could be important for the self-localization applications, and the buildings and parks could serve as like the destination for the navigation, just like in the traditional map applications. So we also have a more detailed ER diagram about our data model and detailed discussions. So if you're interested, you may refer to our paper for the detailed description. And next, we would like to share with you some of our opinions about some of the discussions of our data model, as well as the high definition map itself. So the first one we want to discuss is the capability of our proposed data model with existing data and applications. The second one is the potential simplification for our data model. And lastly, we want to talk about the potential applications for the HD maps other than self-driving technology. So the first one is the model capability. So we are aware that the human drivers will be expected to share the road for at least 1 decade after a large number of fully autonomous cars will be on the road. So there is still a high demand for human-machine interactions, and the existing map applications will be also essential for a long time ahead for those human drivers. And that's why we want to maintain the capability of our model. Oh, sorry. Compatibility with of our model with the traditional applications. So, so we would like to do this by keeping the core entities, edges, and intersections, so that when the traditional applications would like to use this to make use of our data, we will still maintain the compatibility with the traditional applications. And meanwhile, the more detailed data we have in our high definition maps can also serve the existing applications with improved potential features, because for example, the Google Maps provide the application for the lane assistant in certain areas. and the more detailed information about the lanes will help those applications to provide better user experience. The second point we want to talk about is whether we can further simplify our model. So if we assume that we will not have the constraint of compatibility with the traditional node and edge model, probably because that in the future, those new applications will not make use of the traditional data model. So this assumption might lead to a potential simplification for the proposed model that will worth further exploration, because the edge and intersection entities in our data model are just logical grouping of the lane bundles, because we have already composed all those entities with lane bundles, and they do not hold any real attributes in the proposed model. So if we do not have the assumption of the compatibility, we can simply remove this layer. So the last point is the potential applications for HD map data. So the HD map data, actually, we think that it can be used in endless applications. And there are several examples we have observed. So the first example for the applications that could be using the HD map data is that we see that an ongoing research in forestry make use of the Google Street images to identify the type of trees that suffer from certain problems in Canada. And second example is a tree atlas in Southern California that is now being developed based on the Google Earth image data. And we also know that there is a study for the development of urban areas and human migration through analyzing data from different time snapshots. And we think that these kinds of applications could benefit from the HD map data. For example, the study for the trees and tree atlas could make use of the outdoor landmarks of trees in the HD map data, so that the HD map can serve as more or less like a database to provide convenient source of data for those applications. So the main takeaways for our paper is that the rising of self-driving cars technology has triggered an urgent need for the HD maps, but we still think that the existing HD data formats are complained to be not research friendly, so that we propose a standard research friendly HD map data schema by extending the existing node and edge structure in the traditional map data models to maintain the compatibility with the existing applications. And the data model could serve as a generic framework and to add more details in it. So this is the end of my presentation, and I will welcome any kind of questions. Thank you.
Thank you. Any questions? If you have some questions, just unmute yourself and start asking something. May I ask something?
Yeah,
so how do you compare your model with other relevant models? What is the main benefits and
Okay, so actually, as we mentioned in this presentation as well in our paper, the existing data models, so those commercial ones, they are basically like confidential and not public available. We need to be like part of an organization to have access to their data models as well as their data. And also for those data models such as the navigation standard, NDS, the navigation data standard, I think they are complained to be too complicated, or the features they support are for specific applications, so that are not suitable for generic research purposes. For the data formats used by the researchers, they're basically like, if I study the I want to add more data to the HD map, more or less like they will just define part of the data structure for the definition map. For example, they would like, if they try to recognize the landmarks from the statelight images, they might just model those part of the data. So from our perspective, those data models are either like they're confidential, they are too complicated. So we want to, that's why we want to base on the widely used node and add structure, so that the data model itself at the root is more like simpler and can be have the compatibility with existing data models. And beyond that, we can add more information, like the lane level details as well as the landmarks, to serve the new applications. So I think that's maybe the difference of our data model with existing data formats.
Yes, thank you. Other questions? Okay, if not, let's thank the speaker again and move on for the second presentation. So the second paper is about the proofs of the city spatial temporal Twitter content analytics. And then the presentation will be given by Williams Cosmill. So the stage is yours.
I'm here. I'm working on the screen sharing.
Yes.
And open system preferences. Is it possible for you to project the PDF version? My laptop is fighting.
Yeah, sure, I'll try that.
Thank you. Oh, thank you very much. And I'll just say next slide when it's time to change the slide. Thank you, everybody. Here today to talk about some research we've been undertaking at Columbia University. This research is an outgrowth of a high-speed stream processing effort that was being undertaken, and it's in that vein. My co-author, Yunan Liu, is also online to help answer some questions. The title of this talk is Pulse of the City, Spatial Temporal Twitter Content Analysis. So with that, on to the next slide. For a particular perspective on this research, one of the ways we did was very humanistic. So when a person walks through a large city, it's kind of taken as a fact that different neighborhoods have different characteristics. And we were extremely interested in what can streaming online digital data sources tell us about the ongoing activities of a city and actually help to characterize the city itself. Next slide. In terms of streaming data sources, in keeping with the topic of this particular workshop, the great expansion of digital sensing and connectivity offers an invaluable opportunity to better understand urban life in general. We, at the beginning of this effort, looked at a variety of different data sources. We looked at public transit data, bike share data, traffic cameras, social media data, and even use of SDRs to look at RF frequency measurements and the impact of weather. Streaming systems can be architected to support the concurrent analysis of multiple data streams. We ultimately view that as the end goal of this research. This particular paper focuses on the use of social media data, specifically Twitter, to localize, detect, and categorize frequently occurring and anomalous events. With that, next slide. A little outline of what we're going to discuss today. We'll go with an overview of the system we actually developed to process the data. We'll talk a little bit about the data we collected from Twitter, the processing and labeling. We'll then go into how we constructed the machine learning models that are working on that and how they were trained. We'll cover some experimental results. And with that, we'll give some hints into some of the things we're interested in moving forward and some opportunities for future research. And lastly, question and answer. So next slide. Some of the contributions, sort of bottom line up front, we'd like to point out that this particular work utilized and tested streaming social media data to extract urban events. We used a hierarchical category system to do the machine learning for these models. We'll go into that a little bit later. We built a platform that ingests Twitter data in real time and actually does spatial temporal clustering. And we demonstrated the possibilities, which was really the goal of this effort, to kind of map out the art of the possible and prototype a way to look at environments in the urban setting and process them in real time with the streaming system. Next slide. A little bit of context. This is an overview of the system itself that we constructed. We'll go a little bit more into what we saw in the Twitter data later in this presentation. But bottom line, what was constructed for this particular work was a real-time streaming system that was built using the Spark streaming API. It ingests in real time data from the Twitter streaming API, which is basically a real-time API that provides data to a network socket. That data was then taken and temporally aggregated using sliding windows. The period that we aggregated data for this particular effort was 3 hours of duration. That data is provided every 10 seconds, basically to enable it to be interactive in the user sense. The data is then fed in a highly parallelized manner to the dbScan algorithm, which does geographic clustering. To give you a sense of what we're trying to do here, we're taking the island of Manhattan and we're looking at how do I find events that are on the order of 1 city block, and 150 meters is roughly on the order of the size of a typical city block in New York City. We then parallelized the particular clusters, which basically become documents for textual analysis. It's then fed to a hierarchical model which categorizes those events in real time. Next slide. Our basic approach. So we had a basic premise that underpins this research activity. And our basic approach was that we were looking at classes of events that are spatially and temporally bounded. So basically an event is something that has a finite geographic context and a finite temporal context. We then, by appropriately clustering raw tweets based on when and where they were generated, we can generate a textual document that is dominated by a single event. And then we apply machine learning techniques to accurately classify those particular documents. So if you think of it at a high level, we're taking all the data that from all the tweets in the entire island of Manhattan. We're then identifying clusters of tweets that co-occur both in time and in space. And then we classify those in terms of the events we see in real time. One of the advantages of this particular approach, and by that I mean doing the spatial temporal clustering first and then doing the classification, the follow-on stages, is there's an early reduction in the overall workload. It exploits the parallelism that's inherent to Apache Spark, and the online hierarchical modeling scoring that we used increases the accuracy. Next slide. Thank you again. A little bit about Twitter for those that aren't intimately familiar with the particular API. Twitter is both appealing and has some challenges with this. I think we'll get into a little bit later, just highlighting it. It's obviously a biased data source. It includes some events, but not other events. But for this particular thing, we were primarily just trying to get as much information out of the streaming data source as possible. For this particular research, if you look on the right, that's the bounding box that was used. So the Twitter streaming API, you're allowed to put in a geographic bounding box that says where you would like the tweets to come from. So basically we ingested tweets in real time. One of the advantages of this is it's a publicly available data source. It's low latency, high throughput. You can geographically filter. One of the challenges is that it's not location centric. It's fairly well published if you look at the reference below, that only a small subset of tweets are actually contain location information, and that location data can either be explicit or inferred. One of the outcomes of using this data source, if you look at basically the number of tweets we were receiving inbound, just to get, and this is just to give you a sense in a typical day, the island of Manhattan has roughly 1.6 million people on it. Of those tweets, we receive about 60,000 tweets per day that we process. But if you start looking at the resolution of trying to put things into a particular city block, only about 10,000 tweets per day can be placed directly on a map with that sort of resolution. And keep in mind that placement may either be explicitly provided by the user or inferred. Next slide. As I indicated previously, we temporally group the documents and then feed them to the dbScan algorithm, which identifies clusters of tweets. Basically, on the right is an example of clustered tweets from the 4th of July during a 3-hour period. There's about 704 tweets that actually clustered in that particular date and time, and they're grouped into 14 clusters. To give you an idea of how many per day, roughly 70 clusters per day is the number of what we would call events classified in a particular day. Next slide. One of the challenges in this particular approach was creating a labeled data set to basically train the machine learning models. Just a quick highlight of how we labeled these data. It was hand curated. We labeled the data set by hand curating a 10-day period of Twitter content. We took the particular clusters, looked at the raw tweets, and came up with a hierarchical scheme for categorization. It's actually very interesting to look at the nature of what types of content there are in the Twitter stream itself. And one of the things we thought might be interesting in the future is to actually look at it, how it shifts through time. So basically since the beginning of Twitter time. But for this particular time period, we ended up with 5 top-level categories. Informing you can think of as bus schedules, things provided by the government to benefit the public at large. Sharing is people actually sharing particular things with other people. Promoting is much more like advertising, if you think of it that way. Seeking is what you would think it was. It's actually seeking people for employment, so job announcements, things of that nature. And we did include a category of other. As indicated in this particular diagram, for the subclassification, so it's a 2-tier hierarchy, the subclasses, there are significantly more tweets in the sharing and promoting category. And so we went through the resolution of defining particular subcategories for that. And so people sharing photos, people sharing locations, people sharing about sporting events, music events, and so on. This tiered labeling strategy is what enabled us to do the hierarchical classification. So next slide. Just a little factual information about the training data set in and of itself. We trained our machine learning models using a 10-day corpus, which included 729 clusters. Interestingly, on the right, you can see the various percentage of activity. Note that actually a large percentage of things are just regular messages like this bus will be late, the bridge is closed, things of that nature, which fall in the informing category. We were much more interested in the sharing aspect. So what's happening, and in reality, the promoting aspect. To work through how this worked, so basically, once we clustered the tweets into a particular spatial temporal set, we then combined the text from all those tweets and tokenized it to remove emojis, URLs. We then used TF-IDF to identify the key terms related to that, and those are the features we used to train the machine learning model. The machine learning model also included additional features that related to the lat long location and the hour of the day. Next slide. For the actual classification portion, we evaluated 3 different models. Naive Bayes was primarily used as a benchmark. One of the key takeaways from our work in this was the ensemble models, so gradient boosting and random forest, outperformed naive Bayes. So basically there was an advantage to doing hierarchical classification, which essentially means classify at the top level first, and then things that pass the first level get passed to a more specialized model that identify the subcategory. Gradient boosting was selected for the model itself, basically because it outperformed the others in terms of micro precision recall and F1 score. Next slide. In the particular motivation, in the motivation itself, this is just sort of foot stomping why hierarchical classification was used in this particular instance. Obviously, we entered this with grand designs of trying to do some sort of deep learning, and the bottom line is we're constrained by the current data set. So we developed, the training data set is pretty small, it's unbalanced, some categories are relatively infrequent. So in the final analysis, it was better to use a shallow model that was hierarchical, and that achieved the best outcome. Next slide. This is just the confusion matrix comparing, on the left you have when we classify things directly. So we basically made a single tiered model versus a hierarchical model, which classified everything directly into its appropriate subcategory. On the right is when we did the hierarchical, so we classified it into a top level category, and then those were fed on to more specialized models to identify the subcategory. And as you can just tell visually, the confusion matrix was superior in the case with the hierarchical classification. Next slide. Since we're talking about cities and events, we just wanted to give you a feel for what types of events we're seeing and what sort of things we're sensing. So this is an example of particular clusters on a particular day. If you see, there's some interesting observations. Obviously, things like Yankees games and large concerts jump off because there's a large number of tweets that tend to be geographically, tend to have geographic information that co-occur in that particular setting. But there's also some smaller events that you wouldn't ordinarily see. And we see one of the advantages of our particular approach is it looks across all of the content that's being shared everywhere and looks for relatively small events. Our threshold, with less than 10 tweets, we can basically identify a particular event that's occurring in near real time. Next slide. In addition to actually looking at how the system performed with Twitter data, we also looked at the potential throughput of the system from a streaming perspective. One important thing to note, which is sort of interesting, given the small number of tweets that are actually contain geographic information, the actual real world Twitter stream was insufficient to actually stress test the system. So because of that particular limitation, we went to a replay scenario. So we put 50,000 tweets on disk, ran them through a normal 2U enterprise server. And as you can see from the scalability testing, we have a maximum demonstrated throughput of around 1,000 tweets per second. For those interested in broader classification, we were able to actually ingest all the tweets from America, all the tweets globally, without really stressing the system in real time, which is sort of an interesting result. We did want to point out that, I'll kind of dwell on this for 1 second and go a little slower. One of the bottlenecks in the current system is that we cluster everything temporally first and then feed that to the DBScan algorithm second, which basically eliminates the amount of parallelism that can be achieved in the DBScan algorithm. A minor design modification would significantly enhance the throughput of this system, and that would be to do a rough geocoding at the same time you do the temporal coding to enable small clusters, to enable the DB scan algorithm to be performed in parallel. One way to think about it sort of mentally is we're taking the entire island of Manhattan and we're geographically grouping things to the size of one city block. There's no problem with basically saying, for instance, let's do upper Manhattan in parallel with lower Manhattan. It would produce the same clusters, but it would be computationally more efficient. Next slide. In conclusion, we were really excited about this research and for the opportunity to share it with all of you. This research, we feel, demonstrates the capacity of smart cities to serve as a large-scale digital platform that can provide insights into urban life. So going back to my earlier slide of when you're walking through a city, you can feel a neighborhood, you can sense a neighborhood. We'd like to do a very similar thing using digital sensing. Contributions of this specific work include classifying observed Twitter category into 18 particular categories with a fairly high level of accuracy, identifying and observing real, basically clusters in near real time over the first 10 days of the experiment, and actually prototyping the entire streaming system. We are advocating that this particular solution be viewed as a glimpse into the art of the possible rather than an end unto itself, and it could ultimately be leveraged to define the limits of what's ultimately achievable. Next slide. Just a little bit of thoughts about what we could do in the future together. There are opportunities to enhance this particular system. Basically, I think one of the important things is to basically focus on how do we create reference data sets for things of this nature that can be used to benchmark different techniques to each other. Kind of doubling back to specifics. Obviously, we can enhance the categorization accuracy. We can reduce the overall detection latency. I think ultimately the key to this is to integrate additional data sources that will overcome some of the biases that are present in each of the data sources in isolation. We obviously need to do additional work in terms of explicitly addressing system bias and fairness. Twitter is a fairly biased data stream, and how that behaves at a system level should be considered. And also, we would like to scale this up to observation at global national scales. So with that, thank you for your time. I'd like to turn it over for questions. Next slide.
All right, so thank you for the presentation. Any questions from audience?
Hello.
Hello.
Can I ask a question?
Certainly.
Sure.
Yeah, thank you for the nice presentation. I have like the question that you said that Twitter is not like location centric, but at the same time, how did you get the location, like geographical location of each TVs?
Yeah, definitely. You can think of it as almost like, you can almost think of it like we're subsampling. So Twitter inherently, not to get, Twitter itself was envisioned as this platform that transcends space and time. So it wasn't formulated from the ground up, but in the API and the application, people can actually share their latitude and longitude. And then also Twitter, based on places, will do geo-inferencing. So basically, you can do an API lookup of latitude, longitude based on a particular place. So if people tag a tweet with a place, it'll get a lat long. Or if people, particularly people using the older versions of Twitter explicitly agree to share their latitude, longitude. So we're basically looking at the entire set of tweets that come ingested, but we only get the subset that the Twitter API believes it can geolocate to that bounding box.
Oh, okay. Yeah, thank you.
So may I ask one question?
Certainly.
So in the paper, you have been talking about the metadata. So this is about timestamp and the location, etc. And how did you manage to include it in the features?
They are specifically included as, I'll try this and then Yunnan, you can weigh in if I get it wrong. They're specifically included as, basically we took Latin long, we took the max and min of the Latin long for the particular bounding box, and then we vectorized it. So it got turned into a number between 0 and 1 that represents latitude, a number between 0 and 1 that represents longitude, and then also a number between 0 and 1 that represents time of day.
Okay, thank you.
You're welcome. Yeah, and by the way, those are on the end of what is essentially an enormous dictionary of features. Because, yeah, the Twitter dictionary is fairly large.
Mm. Other questions? There's one question in the chat. So let me see. Why did you choose the DB scan over other clustering algorithms?
Yeah, I think, oh, yeah, go ahead.
Okay, I can answer these questions. So basically, there are many different types of clustering algorithms. For them, like distribution-based, central-based, and density-based. The reason why we choose density-based is that we assume that for the high density locations are likely to produce multiple observations of a given event. So in this case, if there are a lot of people that retreat at this place, then it more have a big event or some important event that is interesting everyone else. So we use this density-based algorithm to do the clustering.
All right, other questions?
Yeah, I see one in the chat. It was, as you mentioned, the training data, you manually labeled the tweets. What is the size and how you did it? Yeah, the short answer is we became our own mechanical Turks. The size of it was a 10-day period. We had some, we did it by taking all the Twitter data and clustering it. So actually we only labeled clusters that emerged from the first 2 stages of the pipeline, which helped to, a little bit with the workload. And then we basically, heuristically looked at what the particular clusters were doing as humans and tried to come up with categories that were generalizable enough that they would cut across all of them. But obviously there's a lot of additional work that could be done to refine that. And I think ultimately it would be really desirable to find some sort of more production way to do this so we could have a larger corpus, which would enable us to have higher performance.
All right, good. So let's thank the speaker again and move on to the next presentation. So next presentation is a fuel consumption analytics of driven chips with respect to the road choice. And the presenter will be Ekaterina Gilman, who is the postdoc researcher, University of Oulu.
Thank you, Xian. So, hello again, everybody. I'm very happy to be here, and I'll share with you our short study we did, fuel consumption analysis. And I have a big team with me, so I was not alone doing this. So I thank them as well. Okay. Motivation is, of course, why we should be interested in fuel efficiency when soon we're going to have autonomous driving cars, electrical vehicles, and we don't really probably have to worry much about. But in fact, we do, because even with the electrical vehicles, we still have the resource, such as battery, that requires to be used efficiently, so we have to save it. And of course, in terms of the ordinary cars that still use fuel, so transportation contributes a lot to greenhouse gas emissions. So its amount still grows, as you could see, even though these figures are slightly outdated already. And of course, on the other hand, we do have nowadays great opportunities to measure different aspects of the transportation of people mobility, like magnetic loop data, traffic signaling, traffic cameras, parking. We could use crowdsourcing from mobile phones, for example, etc. and etc. So nowadays cities are getting more and more equipped with these nice opportunities, as well as vehicles too. Also, it's been studied a lot, and we also did this research that it is possible to achieve reduction in fuel economy with the driver awareness. So it's been proved that personal driving style affects a lot the fuel consumption. Also, the route selection affects a lot. And definitely, external factors may affect a lot, especially in countries where we do have rather different weather during winter and summer. So this can really affect the performance of the driver. And we just had this question, how about most experienced drivers of the city? And do they select the routes from like fuel efficiently? Because they know the cities very well, and they probably know the situation within the city, so that they are able to select the routes wisely. So we decided to do this small study to analyze that. Okay, so to approach this problem, we use different data sources. First of all is driving information. Our data set is not very large. We had only 6 taxis, but for a couple of years. And this information was retrieved from the device attached to OBD interface of the car. And as you could see, this was the information we received from it. So basically we have the trip, some basic information about the trip, like total fuel, time of the trip, etc. And then this trip, it actually consisted from number of route points. And these route points are sort of snapshots of the current situation of the car. And then it's provided location information, then current speed at this point, like average speed, and then fuel spent from the start of the trip. So some additional information on the road, how the route progresses. And from this information, we have actually calculated some behavioral characteristics. For example, the percent of the time with the very low speed. So this indicates the amount of stops of the car, or percent of the time with certain speeds, because we know that low speeds, they contribute to increased fuel consumption, and higher speeds, they contribute to reduced fuel consumption, for instance. Also speed oscillations, because these affect fuel consumption a lot, as well as like acceleration, deceleration, how this behavior occurs during the driving. So from this driving information, we calculated these selected behavioral characteristics to understand sort of the driving behavior of the driver. Then we also used spatial data, and for this we utilized the digital map. Digi Road, its name, it's Finnish National Digital Map. It provides different kinds of information about the road network, and here you could see in the figure the example. So we know the pedestrian crossings, we know the type of the road, like motorway, or it's street road, a private road. We know the bus stops, etc. and etc. So we are able to actually retrieve number of interesting attributes about the road as well. For example, a number of traffic lights, or number of pedestrian or bicycle crossings, type of the road, etc. and etc. So we can actually get pretty nice characteristics about the route driven. Then we also decided to take into account traffic situation, because this is one of the important factors when somebody plans the route to take. And for that, we utilized the Oulun service, which is also available for city of Oulu. And this one basically, unfortunately, doesn't provide information about the roads for all the streets, for all the roads in Oulu, but for the selected ones, at least we have this information. And this one is basically has only 3 classes, like smooth traffic, constrained traffic, or like really congested traffic. So we do have this information. So we are able to assign these labels to the actual driven route, because we know this information. And of course, weather is very important factor in our region, because we do have lots of snow during winter, but snow, it's not actually a big problem for driving. The big problem when it's like slippery and when the salt is not yet on the road. So slipperiness reduces the friction coefficient between the vehicle and the road, and then driving is really a little bit more complicated, as well as it consumes more fuel, because drivers have to be more careful as well. And for the weather data, we retrieved this data from Digi Traffic service, and it provides really nice information, not only about the air weather, like temperature, dew point, etc., but also about the road conditions, like how good is the grip with the surface, how much snow or ice or water do we have on the road. So this is really nice source of information as well. Okay, so we've used all this information in our hands to try to understand whether taxi drivers have better selection of the routes in terms of fuel efficiency. And how we did it, so we started thinking that, okay, probably most obvious way is to have the shortest route and quickest route. So shortest route is the road having the minimum distance to travel between a region and destination, so in terms of the distance. And then we also have the quickest route, which actually requires least amount of time to travel. So this one basically depends on the allowed speed of the road. It also depends on the number of pedestrian crossings, traffic lights, etc. So, and we have generated artificial shortest route and quickest route for all the actually driven ones. So we have original route, then we have 2 generated ones artificially with the same origin and destination. Then what we do, we retrieve all the spatial weather and traffic situation characteristic for original routes as well as for this generated artificially routes. And then we conduct analysis like, okay, First of all, we analyze the routes with respect to fuel efficiency and their similarity to shortest and quickest counterparts. For example, if the route which is driven is actually the shortest one, so what kind of characteristics it has, or if it is close to the quickest one, what kind of characteristics it has, or if it is completely different from these two, what kind of characteristics this one has. And the second one, okay, but if, for example, the drivers would select this shortest or quickest counterpart, would they save fuel or spend more fuel? So for that, we had to develop also the fuel prediction model, try to predict what would be possible fuel used in these artificial routes. Okay, and when we try to compare, okay, if we want to compare the actually driven route with its shortest counterpart or with its quickest counterpart, how much different is different? How can I compare those? And we did some research on that, some reading on that, and we decided to use the overlapping coefficient for this sort of situation and then just define some thresholds. Like, okay, if the routes overlap more than 98%, then we consider them as the same. And we also consider the routes quite different if they overlap less than 80%. So, and with these boundaries, we ended up to this certain number of trips for analysis, like same as shortest. So it means that these routes are more or less the same as shortest one and same as quickest. Then we had number of trips which actually equal to both shortest and quickest. And then we have a bunch of the trips which are completely different, or at least different more than on 80%. Okay, so we actually analyzed separately these behavioral factors, then route characteristics factors, and I have written some conclusions from this analysis in the paper, plus we have a little bit more comprehensive representation of our results as the supplementary material which is available with the link of to the paper. But basically what we can see here is that actually driven trips, as indicated here, if we talk about behavioral analysis with D, they demonstrate a little bit, the different trips, they demonstrate a little bit more proportion of low speeds when compared to the trips which are similar to shortest or quickest or even the same trips. So this was quite interesting finding as well. And it's completely opposite for fuel efficient speeds, which is considered, for example, speed from 50 to 70. So of course, like the quickest one, they demonstrate larger proportion of these because these are mostly driven on motorways when compared to the rest of the trips. And the different trips, they again here, they demonstrate the little bit poor results when compared to the rest of the trips. Also, it occurs here that shortest and these different trips, they show a little bit more difference in speed oscillation when compared to the rest of the trips. And this is clearly explained with the template. I'm a little bit disturbed. And okay, thank you. So, and this can be very well explained by the placement of the trips to the actual roads. Probably it's not very well seen here, but for example, quickest trip, similar trips as the quickest ones, they follow the motorway roads and very main roads of our city, which is actually a wise choice, of course. And the shortest trips, they contain mainly not main streets and local private streets. which makes the speeds again here a little bit slower. And however, like similar to both, and both like different trips, they possess very different patterns here. So they actually occupy different kinds of routes as well. Okay, am I moving? Yes. Okay, so if we move to analysis 2, so what if drivers follow shortest and quickest counterparts? Well, first of all, if we try to compare the distribution of the trips, how they overlap with quickest and shortest counterparts based on the route distance. So we actually can see that starting from maybe 7.5 kilometers distance of the road, we have more and more overlapping with the quickest routes, which is of course straightforward in terms of the geometry also of our city, because it's built so that it's much easier to get from like south to north, for example, if you go directly to the motorway and then you just go to the other roads. Otherwise you like really have to go through the city center, and it takes lots of time and troubles as well. And if we try to also compare the spatial characteristics analysis, this pretty much resembles to the results retrieved before. So we can see again that the quickest generated trips, they take much less or considerably less low speeds routes than compared to the rest of the trips. Interestingly, observation is that actually driven trips, they take more turns to the right or to the left than generated artificially routes. So that was interesting observation that we have found. Okay, so but in order to answer to this question, we had to try to predict how much fuel would drivers actually spend if they could drive to this shortest or quickest generated counterpart. And for that, of course, we couldn't use the behavioral features completely, because we can't really know or can't really assume what kind of driving would be then on these roads, how much stops there will be, and how would be the speed oscillation of the driver, because it's very like human also related thingy as well, not only the situation of on the roads. So therefore we had to let this out and include only spatial characteristics of the route together with weather and traffic situation. And we used a boosted regression model here to learn to try to predict the fuel. And as you could see, the model is not the perfect one, of course, because particularly we use only route characteristics, timing, and weather and traffic situation, which is a little bit difficult to actually evaluate the fuel, which becomes also directly from actions of the driver. But nevertheless, so we at least received some interesting assumptions about which factors actually contribute the most here to the fuel consumption. And we could see that definitely time of the driving is important, which somehow could reflect also to the driving behavior. So when we have rush hours and when we had to like idle a lot on particular spots of the city. Then crossings appear to be important, turns to the left and to the right. Also, % of the trip driven on 40 kilometers per hour speed limit road. This is directly related to the slow speed driving, which actually negatively affects the fuel consumption. Traffic lights, which is also something that common sense tells us would affect the fuel consumption. So that was sort of also interesting to see. All right, so now we do have a model. So let's try to compare it with the results. So we do have actually here the situation that in case if we have actually driven trips here, then we know the actual fuel here. So then we also applied the model here to get the modeled fuel here, and then we find the model for quickest generated trips and for shortest generated trips. So in terms of the liter per kilometer, we don't see any significant difference, statistically significant difference between these numbers here. But then of course, I mean, if you compare the actual value with the model, is a little bit differs here, but the distribution is a little bit different here. So this also shows the problems of the model. However, when we multiply this to the whole length of the route driven, then findings are quite interesting. So we again split here to different routes. So we do have also shorter routes here, and then we have longer routes like more than 17 kilometers, for instance, here. Interestingly, so we see that driven modeled, we don't really, because I think this is something where we do actually compare, because we can't really compare with actually driven. So driven modeled consumed more fuel when compared to shortest one and quickest one. So this in fact tells us that maybe if drivers would follow the shortest path or quickest path, they could in fact save more fuel than if they would drive as they drive. So that was quite interesting also. And here we have also the median savings for different distances calculated for both shortest generated and quickest generated routes, which quite confirms to related studies. I think so. In related work, the economy lies somewhere between 8 to 10%. So I think it's somewhere in line with existing research. Okay, so main results. So in our data sets, well, it's not the large one. I remind you, we had only like 6 taxi cabs there. So the trips different from both shortest and quickest counterparts appear to be less fuel efficient when compared to the trips following either the shortest or the quickest route. Obviously, we found the differences in route characteristics and corresponding driving behavior. That was nice. Then also analysis of driven trips and their generated shortest and quickest counterparts revealed that longer trips rather follow the quickest counterpart. So, I think that we already discussed that in our particular region where the city is a little bit stretched through north and south. So it's the most logical way to travel. Also, we were able to identify what kind of spatial characteristics affect the fuel consumption the most, at least within our circumstances. And also based on our model predictions, so the driven trips, they demonstrated actually worse fuel efficiency when compared to artificially created routes. And also some research, for example, says that a fuel efficient route is often similar or close to the shortest one. And in our case, the distance actually plays also a huge role. So for shortest trips, actually the shortest are usually more fuel efficient as well. So it's also supports this research at least. Yes, I think that's it. Thank you very much.
All right, thank you. Some questions from audience. All right, so if we don't have more questions, let's move on to the next presentation. So next presentation is about public and open Internet of Things for smart cities, the SME perspective. The presentation will be given by Ella Peltonen, who is a postdoc researcher in University of Oulu. Ella, the stage is yours.
Thank you. Can you hear me okay?
Yes, we can.
Great. I'm just putting this to the full screen. Okay, cool. Thanks, everybody. Very nice workshop for now. I'm giving here a little bit different talk today. This is very non-technical topic, but that's due to the story here is that we had opportunity to have a student from this management engineering and business side, and he's the first author of this talk, Pekka Okkonen, and he has luckily left the industry and working after his graduation, so that's why I'm giving this talk. So this is a pretty different thing I usually do. I usually work with more technical and data-driven side, but this time we are a little bit looking for the value of Internet of Things, and especially public Internet of Things for SME corporations. So yeah, the open IoT platforms, there are multiple ones, and many of those are used for different sort of pilots and pilot projects. And many of the cities being interested in this development of getting the smart city status, many of the cities are claiming to be smart, not necessarily yet very smart with the technical way. So we can still say this is an ongoing development. The current focus being given to the cities and municipalities and those people in the cities, but we would like to highlight that also the enterprises and corporations are important part of this development, not only as a providers of the technology, but also stakeholders that try to make a business in the open IoT platforms. So to give the kind of prerequisites for this, we do have an open data, that's the target. We have an open source code, that's the target. We are aiming for those. So the main question in this talk and this work is to generate a value to all. It's very clear sometimes to customer side that the value for cities, value for the people living in those cities, but what's the value for the corporation side, and not necessarily only the monetary value. For example, the small businesses, small enterprises, micro and micro side enterprises, when they are participating in a smart city development and these pilot studies and participating in open IoT projects, what's the value they are gaining, and what are their main challenges and main issues in this development? And that was the main research question we started to look with. And we wanted to have a qualitative study. This is a slightly different. I don't usually do that by myself, but because I did have this experience and skills of business management engineering student to utilize during last summer, and he did his thesis about this, and we wrote a paper because the results were interesting. So this is not necessarily a project we are continuing after this paper, but we know that these results are worth of releasing and worth of publishing. So we wanted to submit this paper anyway. So there is no data like quantitative data in this study, but we have a lot of opinions. We have discussed with the corporations. We have asked real companies to provide their real experiences when they participated in their IoT pilot studies together with the city of Oulu and University of Oulu and a couple of other universities. And that's why we conducted the interviews to get those real gains that can be hard to measure actually, because if you have a corporation of a couple of 10 people working in there, it can be hard to actually analyze the gains in a monetary way. Because they have a different states of development as a corporation. They have a different states as a startup or a small business. So it's not always clear how to measure the monetary value. And that's why we wanted to ask them to provide all the other aspects of the value they may gain from participating in the open IoT studies and open IoT development. So these lessons we wanted to learn when we started doing the questionnaire and we started doing the interviews. We wanted to ask them whether they see any value other than a monetary value from sharing the data, whether they feel it suitable business strategy of using the public data, considering you have to provide sometimes something as a result of getting the data. How they feel using the open platforms when developing the products, and especially open source platforms, which are usually kind of go-to solution from cities and municipalities being free of use, of course. So how the small businesses felt like participating on the not only open data studies, but also open source platform studies. And of course, we were also interested in these co-creation aspects between the cities, municipalities, a university, or research institutes, and the small corporations participating in these studies. So the companies we choose for the study, they were all the companies who participated in the same time that the pilot studies in the research project. They are all located in the Oulu area in Finland, where we are from. They are all micro-size, but they are expecting to grow and became in the, how to say, small size enterprises, not anymore a micro-size. And those are all companies that has a very good future as seen in the future. So we are expecting these products to become important, and also the different stakeholders in Finland are expecting the products to become growing and became bigger. And at the state of the interview that last summer, they had all less than 10 employees, but as I know, at least some of the companies are already getting bigger and they are hiring more people. So very small and very easy to approach on that way, so that very easy to organize questionnaires, or interviews, very easy to actually have a chat with the CEO, instead of going through multiple secretaries. So that was also important discussion between two companies and the research institutes, that how they feel and what kind of feedback they get from the participating in these stories. So the pilots we conducted, the project with these pilots were a part of were called the City IoT, where the aim is to build open sourced open data platform, where the basically city puts the data on the platform, as well as the companies participating, and then the companies can get out of the platform both of the city data and the data from other companies to co-create this sort of general urban city database. And that's the aim of the project. The companies we choose to include the interviews, the 4 companies, they are anonymized for the study, so that's why I'm not mentioning the names. One of those is working for 3D visual solutions for urban planning, and they have a lot of data about the 3D imaging. Then we have two companies making this kind of complete IoT solutions with the specified sensors, basically meaning that they have developed or engineered their own sensor that they are using to provide an IoT solution based on that sensor. And the fourth one is this kind of data transfer company providing a platform for data transmission. These are the companies, and the platform I mentioned, we did have this a European level platform called Vivar. Not going on very much in the details of this platform. It has its cons and pros, but this study is supposed to be not limited only to the platform itself. So what we learned from the interviews we conducted, and also by following the pilot procedures during the summer, where these companies were participating actively on the pilots and also finishing the work within them. So one of the topics we wanted to discuss was the data, because the open data is often seen like a kind of holy grail, that you give them open data and then everybody's happy. But in this case, we learned that it's actually the biggest value is coming from the data combination. So that's that we have an open data set provided by the city or cities in some cases, and then the company has their own database. The combination is not always necessary to create any products, but it can provide opportunities and that's kind of additional value. Quite understandable result that when you have more data, you probably have more value. But the main key here is that not the data itself is not what gives the value for the companies, but these methods you use for pre-processing and structuring the data and modeling the data. So even before running any fancy machine learning and AI algorithms on top of the data, the companies see the value of the pre-processing paradigms and methods to get the information out of the data before we are running it through the analysis system itself. And so in addition to having like a raw data and analyzed data, the interviews highlighted the importance of this pre-processed data, what comes after the raw data, but before we are actually applying any learning algorithms on top of that. And those, most of the small companies highlighted, and this is very relevant to all of their business strategies, is these information products. So the goal is to combine these processed data, whether they are coming from the open data sources or the company's own data sources, and generate information products that offer the increased value. So the value is coming from the information, not of the raw data itself. And that was very crucial. It may sound very straightforward, and it's something that common sense can get up a little bit. Of course, that sounds like clear to everybody, but it was nice to see that highlighted in all of the 4 companies we interviewed, and all of the 4 companies mentioned this is the most that makes them differ from the other competitors, is to get the better information products. And that's kind of shaping the whole industry. So we are not anymore discussing about the engineering products, or we are not only discussing about the data models, but information products that are more high level products and provide more value for the companies and for the market also. About the platforms itself, so these are the general comments about using any IoT platform which is open sourced, or not only the Vivar platform we used in our pilot. So we were asking also other opinions, and some of the companies are part of our study were also participated previously in other open source projects, so they did have an experience about the multiple open source platforms. And the main issue here was the life cycle of these projects and life cycle of the open source projects. and being here and looking for those companies who want to react something in next 5 years and next 10 years and really build a company that has a long history also in coming, it's very clear that if they can choose an open source platform, they need to trust that it's going to be developed and run for several years to come. And that was the main issue here. And of course, when giving out the data, the companies felt like getting the public open source data is okay to everybody because it's collected by the cities and municipalities or governmental bodies. But when they are handling out their own data, they want to get something out of it. So that leads to the discussion to the pricing mechanisms of sharing the data. Should everything be free? What the cities can actually provide in addition to the open data and open platform that are open by definition, what else they can provide so that the companies became more interested in actually joining these open source, open data systems or environments, or so they need something in return. They're happy to provide their products for a change of the data, but if they want sharing their own data, it's very crucial that they feel a value of sharing the data, that they feel that there is something they get back from giving the data out of. And that's this is a quote from one of the CEOs of the companies. It would be utopian to think that someone would just measure data, meaning collecting their own data, their own sensors, and push it to the platform out of kindness. So this is the raw reality that, of course, these companies, they want to make business, they want to make money, they want to create something that's actually possible to sell. And that means that they put the hard work and efficient hours creating the data. They want to get something out of it when they are sharing it. But they were happy to share it if they can see the value they are generating from the data. So about the pilots themselves, and most of them companies, they saw that there are actually possibilities to generate these kind of remarkable business ideas when participating in the pilots within the public sector. But of course, they were also worried whether these, what's the life cycle of these pilots. So you can get an ideas out of pilots, but can you get a real products? And do you have a market for those products created on the pilots? But there, of course, the role of the public sector, the governmental body, the cities were seen important because the pilots gave a possibility for companies to actually participate in something within the public sector, within the cities, and collaborate with the cities. However, for looking for the lifetime of these projects and lifetime of these companies and their business strategies, they were also worried about this middleman effect, having the data transfer to happening between the public sector, the cities, or the private companies. And one problem here was seen that these are tied on the research projects, which are funded by the research institutions or EU or NSF or local business corporation supports. So whenever there is a research institute, which is a little bit like a middleman, and the project ends, does the collaboration continue? That was the biggest question. So they felt like the support of the research universities and research support was very great. And they felt like they got a very valuable contacts to the public sector and the cities, but they were also feeling that is it a good idea to have a university as a middleman here, because when the project ends and the university leaves, the products should still be continuing being used, and they were a little bit balancing about value of getting information from the universities, but being too tied of these middleman sort of partners in between of the actual data providers and the actual product providers. But also interesting was that all the companies felt like they had a surprisingly few technical challenges, whether they are related to the platforms themselves, data management, data sharing, And usually these technical challenges are kind of like highlighted in the lessons learned from different IoT products and IoT pilots. But in this case, most of the companies, of course, they are very tech-savvy. They are very into IoT technology. But they highlighted this, that the nowadays technical problems are always solvable. It may take time, but they are solvable. So this wasn't the big issue. So the technical support wasn't the main value, but instead they saw the value in actually information gain and the gain they get from the different partners, the information and knowledge, the latest knowledge, instead of the actual technical support. And that also means that because a lot of technical support was put in the project, that was most of the time that wasn't needed that much. What they needed was information knowledge to make these information products they are using. So that was one important lesson learned. So we identified some of the open challenges. And my message here is to a little bit like give these challenges for you whenever you are running projects together with the corporations, together with the small businesses or cities, to look at the IoT challenges and solve these challenges before you start your project to make it more successful. So consider the life cycle, because that was the most worried issue of all the companies involved in the project. When the project ended, what's kind of the life cycle of the product? Products they have developed in the pilot, what's the life cycle of the open source platforms themselves, and what's the life cycle of the data? Is it the data available after the project at all? Where will the data end for? Where is it stored? Is the storage available? So lifetime and life cycle, what happens when the project ends? That was a very crucial question for most of the companies. Communication. So this basically means the inside communication of the projects. So the companies were especially, they wanted to create direct links between them and the cities or municipalities. They wanted to create a strong network where the information sharing is kind of natural, it's not forced, where people are happy to share information and knowledge. Most of the technical problems were due to missing technical information, like how is some sensor placed in the location. If sensor is sensing like a building or something, it's very crucial to know where in the building the sensor is and things like that. So the missing technical information and hardness to get in touch those people who were actually providing the technical information, or whether it was at all written down. So the communication becomes a very crucial for successful open IoT projects, whether there are universities in collaboration or not. But of course, when the university is there, and university's role is often this kind of communication and knowledge sharing, so that easily is the role the universities can take. So taking care, the communication is there. And most of the errors and mistakes we did were due to the human errors. So the most important mitigation plans for failures and errors are due to the human errors. And that's one of the main lessons I want to share today. And of course, we need to discuss about the monetary issues. So of course, the companies feel that even if they get the free data, they want to sell the product for money. So there is this discussion balancing whether it's clear to everybody, even if they get the free data, they have to sell it. So the monetary value and generation of the monetary value has to be defined before the project actually starts. And maintenance administration costs, these are related to the life cycle of the project and life cycle of the products. So whether the maintenance and administration, for example, is covered during the project, if it's not covered anymore after the project, the small businesses that doesn't have the backup for the maintenance costs may have a problems, and they may have to get out of those products that had a good ideas, but they give them a living. So these are also related to the life cycle issues. And what happens after the pilots also in a monetary way. So the value, clear value here was this a long-term life cycle, looking for life cycles in general. And that's what they wanted from in participation of these open IoT products. So to summarize, these open and public data sets, yes, they really provide opportunities and create additional value for even for small companies, and especially for small companies. And most of the small companies we are happy to work with, they were very enjoyable in collaboration, and they enjoyed the collaboration with us too. But those what they learned and what they feel that learning, the value of learning here, processing, cleaning processes, and knowledge of the information retrieval from the data, not only applying and machine learning indirectly, but also those knowledge of how to pre-process the data, how to get the statistical information out of the data, how to understand the data, how to learn to read the data. Those issues were what the companies felt like they made them to stand out from competitors, also from the future. And that was the value they gained from the universities and research projects. So very short talk today, not have that much more to share. If you are interested in reading the paper, it's hopefully somewhere in the proceedings already, and that's more about the lessons learned. I'm happy to take any questions if I can answer them, but most of the study was run by my student Pekka, who did a very good work. So I can, if I cannot answer the question immediately, you can send it me by email, and I can put you in touch with Pekka. So thank you everybody for listening. This little bit uncontroversial talk today.
Thank you very much, Ella, for this interesting presentation. Do we have any questions, comments? Maybe I can start so that you have a little bit more time to think. So could you hypothesize, because you don't have the data at this point, but you've been working with smaller companies. Yeah. Do you think some aspects could be considered differently by companies if these are like bigger ones with a little bit more closed and regulated practices and rules, etc.?
Sorry. Yeah, of course. For example, the risks of participating, the maintenance costs and stuff like that are not that big issue for the bigger corporations, because they have more freedom in a monetary way and resource way to actually try and test and maybe fail. But if you are considered a small company, they put a lot of effort when they are participating in a research pilot, because that means they probably tie their whole personnel to the project. They don't have extra resources, and they are more worried about what happens after the project. And they are more risky in terms of they have to be successful. If you have a big corporation, you can participate in projects kind of like I'm not saying these projects are not important for big corporations, of course, but they can more participate on without taking the monetary risks or business risks, but maybe just kind of like interested in gaining new information and gaining new ideas. But for more smaller companies, these are like life and death questions, really.
Yes, right. And these companies that you have interviewed, have they worked already with open data by themselves in their like production of their information products?
Yes, these interviews were made in the end of the pilot section, so they were working in 6 months projects before we did the interviews, or depending on the company, somewhere interviewed in the 4th month or somewhere interviewed in the 6th month, but they were working in a 6-month period within the project and within the pilot, so they had gained already an experience of running. And this project started, like we did a lot of course, analytical work and more papers to go on that side, but we had this student, Pekka here, and he was interested in making this. He was mainly doing the interviews about collecting this general feedback data, but because he started asking questions about the values, we decided to make an actual this kind of business management questionnaire for the companies, and he ran that, and he did a thesis about this too. So
yeah, that's also interesting to see how the companies consider these issues as well, because researchers have their own always track and thinking maybe. I don't know. Yeah. Interesting. So
Thank you.
anything else? I don't see any questions in chat. Okay.
There is a private question for me.
Okay, go ahead.
I can read it. Where any data source is discussed that would benefit multiple business case, would benefit everyone, but on one small business could afford to do it. So yes, the data we collected and what the cities shared were, for example, air quality data, data from energy consumption in different parts of the cities. Then they had public city buildings, for example, schools and other office spaces, and they collected all various different data sets from those places. And one very interesting thing, for example, where they had these pressure sensors on top of the roofs, so they measured the pressure of the snow during the winter and stuff like that. So the data was very general purpose data. And all of the companies, when they were developing their own pilots, they had an access of all the data. And they also shared their own data, but we didn't see a case where one company shared the data to another company that used it, because most of the companies, they shared the data publicly in the very end phase of the pilot. But that would be, of course, a more interesting use case. So answer is short answer is yes. Yes. Thank you.
All right. So let's thank Ella. Thank you, Ella. And
thank you.
Yes, so let us move on. If your guys feeling all right and don't need the break, like short one. Or at least no action in the chat. So I assume that we can continue then to the next presentation. And it is Proactive User Engagement by Friendly Survey and Data-Driven Methodology by Paulo Betas. So please, the stage is yours.
Good morning, everyone. I hope you can hear me.
Yes.
So do I need to share my screen or we use
Yes, please. There is like this screen sharing button.
Okay.
Yes.
Can you see my presentation?
Yes.
Okay, fine. So good morning, everyone. I am Paolo Betas from Politecnico di Torino, and I am glad to present here our work titled Proactive User Engagement via Friendly Survey and Textual Data-Driven Methodologies, co-authored by Riccardo Callà, Tania Cerquitelli, Claudio De Giorgi, and Arianna Montorsi. In our paper, we present Carol, a new methodology able to collect user feedback through speech recognition, convert audio messages into text, and analyze them through text mining techniques. Carol also offers first graphic analysis in real time, while more complex results are shown in a second moment. As a first use case, we test our methodology in a public event organized by Politecnico di Torino about a gender minority in a university. The results obtained in this event are good, and we believe that this methodology can be extended to other urban contexts. A smart city is a municipality that uses information and communication technologies to increase operational efficiency and improve both the quality of services and citizen welfare. In all the services offered within a city, the most involved and directly concerned people are the citizens. They play a key role in the city's economy, and for the reason, their judgment is fundamental. Based on this citizen-centered perspective, smart cities should consider the needs and perception of citizens to be able to redesign their urban scenario through innovative urban services. This operation can be done by collecting and analyzing the citizens' opinion, their thoughts on a specific topic, and their advices. To do this, the easiest way to collect citizens' opinions is through a survey, a process that consists in collecting the participants' answers related to a specific question and, in a second moment, analyze them. We now present Carol, a new non-conventional survey methodology. Our methodology can be divided into 4 successive steps, and these steps are the data collection, the data preprocessing, the real-time analysis and visualization, and the in-depth analysis. As shown in this slide, our methodology differs from a normal written survey. In fact, in this case, each participant is asked to answer the question through a microphone. In this way, we exploit the fact that expressing an idea through a verbal form is more natural, easier, and faster than the written form. Each message recorded by a client is then sent to a single central server, which collects all the audio text. Then the server converts each voice message into a text message thanks to a Google API for speech recognition. So at the end of this step, all the answers of the different survey participants are in textual form. These text messages are particularly well suited to be analyzed using text mining techniques to discover useful information from them. And to perform this analysis properly, each text message must be processed in order to make the textual data analysis problem more efficient. In particular, each text message is processed using the 4 analytics steps shown in this slide. First of all the punctuation is eliminated and all the uppercase characters are converted to lowercase. Then the text is segmented into tokens separated from each other by a white space. As a third step, the lemmatization allows to group together all the inflected forms of a word, so they can be analyzed as a single item. Finally, stop words are removed from the text. Stop words are those words that do not provide any useful information to the text contents, and they can be words with no meaning, like preposition or articles, for example, or words widely used in a given context, which do not add any useful information in the analysis. In our methodology, we decide to add the words contained in the survey question to the list of stop words, because the participants answering that question are very likely to repeat those words often. After the preprocessing phase, the first real-time analysis can be shown. The analyses are visualized in a dashboard like the one shown in this slide. These results are shown real-time during the survey, and each time a new message is recorded and processed, the graphs are updated. The dashboards includes 3 graphic objects. The first graph is a word cloud showing the most significant and frequent words. The more important a word is, the bigger it is inside the cloud. And the importance of each word is defined by its weight, calculated as the total number of times the word appears in the messages multiplied by a term that is the number of messages in which the word appears divided by the total number of messages. The second graph is histograms, which for each predefined topic show the number of words associated with that topic and the frequency of each single word. Finally, the third graph contains histograms that show for each client the number of voice messages collected separately. After all the audios have been collected, more in-depth analysis can be applied to the data converted in text. Due to the computational cost of the proposed techniques, The results cannot be shown in real time, but only in a later moment. The first of these techniques consists of identifying bigrams or trigrams within messages that are those pairs or triplets of words that often appear together in the text, and for the reason they are considered as a single word. In this way, the final word cloud is also updated, taking into account these new words. A second analysis tries to identify the main topics within the messages. If the number of data collected is large enough, text clustering is applied using TF-IDF to obtain the weighting schemas and applying the k-means algorithm after setting the best k-parameter, analyzing the silhouette score. K-means divides the messages into k-subgroups, each of which represents a different topic. If instead the number of data collected is small, singular value decomposition is used to reduce the dimensionality of the dataset in n components, each of which is obtained as a linear combination of the original columns. The weights associated with each word in the linear combination allow us to assign each new component to a specific topic. Finally, using the DB-scan clustering, a density-based state-of-the-art algorithm, we are able to identify those messages that are classified as outliers by the algorithm, and therefore contain words and concepts not used in the other text, dealing unique themes. The methodology proposed in this work has been tested for the first time in an event organized by Politecnico di Torino and addressed to female students, with the aim of collecting their ideas about new services and opportunities that can be offered to deal with the problem of the gender minority in STEM, that includes science, technologies, engineering, and mathematics subjects. The event was called She Acts Polito, and it was the first meeting of the girl studying at the Politecnico di Torino. We believe that the considered use case is an interesting proof of concept in the smart city context. In fact, a public university as Politecnico di Torino assumes a key role within the city, since attracts a large number of students who leave the city and exploit provided services. During this event, 101 female students were asked to answer a specific question by recording a voice message on a dedicated client. The girls were placed in a university hall with 8 client devices communicating with a single server. When the clients started recording the participants' audio, a dashboard including the real-time analysis is shown on the classroom screen, and it is updated every time an audio is processed by the server. When the event took place, the histogram shown in the dashboard had not yet been integrated. So at the end of the survey, the dashboard was like the one shown in this slide. From this word cloud, we can see how the verb to create is the word with more importance, probably used in sentences like create an event or create a meeting. Then, at the end of the survey, more in-depth analysis were performed. Since the number of data collected was not big, we identified the most frequent topics in the various messages using the singular value decomposition. SVD allows us to find 3 topics shown in this slide in a word cloud form. First topic highlights how most of the audio collected is focused on the new experience within the first year of university compared to the old world of high school. The second topic is focused on educational team, showing the desire of the students to pass their exam successfully. And the third topic highlights how important it is for students to have a moment of aggregation, spending time together, also in a friendly way, like in sports activity, for example. Even if these three arguments found give us a good general overview of the topics covered in the various messages, in this case, it is also interesting to report those messages that do not fall into these common categories. Because of their uniqueness, these messages can sometimes highlight innovative and out-of-the-box ideas. The outliers messages found using DB-scan algorithm are the two shown in the slide. The first message talks about the discomforts of women's toilets in the university, while the second is about the possible need for a psychological service for female students in the university. We have now presented Carol, a methodology able to collect and analyze participants' opinions, giving them maximum freedom of expression. Future improvement of what we have done so far may be the collection of heterogeneous data like images and videos. Moreover, Carol could also be tested in a different and more crowded context within a smart city in order to evaluate its global performance. Thank you very much for your attention, and I am glad to answer your questions online or in the chat.
All right, thank you very much for your nice presentation and work. Do we have any questions or comments? We should have NLP experts here, given from the previous presentations. Maybe I'll start so that you have a little bit more time to think.
Okay.
So you have presented this nice system to collect the audio feedback and to show the results immediately. I wonder, do you see any challenges or maybe limitations, or in which cases maybe this approach has some limitations or challenges? So could you comment on that?
Okay, thank you for your question. And in our use case, we didn't find any limitation in collecting audio tracks, but we consider audio messages more a more general dialogue to express people's opinions. So we think that the freedom of expression of the participants is higher in audio than other forms of think like, for example, text.
For example, if this is like big public event and there is some noise, is there any challenge that maybe this can be not very well recognized or something? Have you done this kind of experiments?
Okay, sorry, if you talk about noise in the registration?
Yes, for example, there is like noise around me. Does it give any problems to recognize the text?
But in our case, we use 8 client devices, and obviously these clients have to be distanciated from each other, so the registration cannot have interference from each other. But obviously this is a good point, and this is we have to consider these distances from client devices. In our methodology, in our theory methodology, we didn't define a fixed parameter to a fixed number of client devices in our registration, but maybe in future works we can discuss better this parameter.
Yes, thank you. And I also would like to comment. Of course, inspection of outliers is really important, and in particularly in this case, I mean in NLP, it gives a
Yes.
completely like new aspect. So I just would like to mark this, that I think this is quite interesting.
Yes, yes, yes. Thank you. I also think that out of the box ideas in this case was of particular interesting.
All right. So I don't see any questions in chat. Anybody? Anything? All right. So we do have a question. So is it applicable to other languages too? I assume your algorithm in Italian. So Bakthior Nosir asks.
Oh, okay, thank you for the question. And our methodology, or maybe our tool was developed in Python using Python programming language. And Python provides us a library, and this library is set in Italian languages. So now all the audio are collected in Italian languages, and also in our use case. So in our test, all the participants speaks in Italian. So we didn't consider the case of more languages, but in the future it isn't a problem to change this parameter, giving the possibility of speaking in different languages. The only problem I think in future works of giving this possibility is, for example, the word cloud, because or the word cloud is only in Italian languages, or it is only in English language. Mix the two results, it could be problematic. I hope I answered your question.
Yes, thank you. Okay, but if there is nothing else, thank you for the presentation again, and let us move on to the next.
Thank you.
So now we have Think Cities, the Accelerator for Sustainable Planning by Gwenal Carfantan. So
hello, could you hear me?
Yes.
Okay, I will share the screen. Okay. Could you see my screen?
Yes.
Okay. Hello, everybody. My name is Chung Dũng Lê, one of the author in this paper. Our paper is Think City, the accelerator for sustainable planning. Today, I will talk to you about our paper, the Think City. The Think City project aim to develop a digital tool for smart city. To evaluate the urban project. A proof of the concept has been developed in partnership in Rennes Metropole. For the context, the territories are facing increasing pressure on the sustainability for the development projects. With their environmental, social, economic, technological impacts. Besides, the data produced by various devices involve transportation, service, social mix or the green space. For example, this figure shows the air indicator for in an area with the score of NO2 is 5, and the ecological impacts is 4. Other example, this for this figure show another example with the rainwater management indicator. And with my presentation has 5 parts. The first is the introduction, and the second part is will describe about the Think City project, and the third part show the WAP10 platform we used in our project, and the fourth part show the form-based semantic catching methods used in Think City project, and the final part is a conclusion. Let's begin with the existing tools. There are more and more offer about smart city application, such as visualization solution, LensSim 3D, and the raw data reading MCMA. And with this table compared with many existing tools and the Think City, and the Think City is distinguished by its global approach for the point of view of the subject evaluated. And in such a context, the problem is that how to exploit the growing amount of data available. There is a lot of data, but they remain difficult to exploit. The raw data, heterogeneous format, or difficult to access. With motivation, the Think City aim to provide a significant time saving for user in their daily tasks. The valuation of the data produced and the response immediately crossing various data sources. With the motivation, our proposal is that we would like to evaluate or compare geographic area according to reference indicator, and simulating the impact of the new development, recommend the adjustment, demonstrate the additive of the territory, and we would like to integrate dynamic data on some existing indicator and the new indicator. And the second part of the presentation, I would like to show you an overview of the Think City. The first, the Think City is able to define an urban project with 6 core values. The first is water management. The second is energy and climate. And the third is societal approaches and mobility, accessibility, ecosystem biodiversity. And the final is water management. For example, this figure show an example of a traffic indicator of the Rennes metropole, and another example will show you the waste indicator. Moreover, the Think City can provide increased value such as approximately of the service, health, risks, or carbon footprint. This figure show an overview of the Think City project. is considered two main classes of data sources, the pure static and dynamic data. In particular, PostgreSQL is used to manage pseudo static data. And on the other hand, the WAP10 platform is used to manage the dynamic data. The third part of my presentation is will show you the core platform, WAP10. It is built to manage and process the time series data. This figure illustrates a geo-time series with the header introduce the class and some label. And the second part is the data point consists of the timestamp, a latitude, longitude, and evaluation and a value. And the final is the bottom part provide the key value pair. This slide shows the WAP script and the WAP10 platform. WAP10 platform dedicated analytic language called WAP script. The first WAP script is a data follow programming language. The WAP script provides more than 1,000 functions ranging from simple statistic to complex algorithm. And the WAP script language is also integrate in many existing data processing languages and environments such as R, Python, Zeppelin, Jupyter, Spark, Pig, Storm, or NiFi, with the ability to use the same WAP script code across all the environment. This script shows an example of WAP script. The first data is read from the Gulf no aa.storm.wine wide catalog from the 1st of January to the 1st of February. After that, the data is calculated in the function of mean and budget type. The fourth part of this presentation will show the form-based semantic caching. It's relies on three phases. The first is a form-based query, and the second is semantic processing, and the third is time series optimization. For example, this example will show you the form-based semantic caching methods. We assume that the query is formed into select timestamp, aggregate value from area A from T1 to T2, and the cache has the result from the 1st of February to the 5th of February, and the other result is from the 7th to the 10th of February, and the incoming query is required the data result from the 1st of February to the 10th of February. So this query is divided to the probe query and the remain query. The first, the probe query is optimized in the semantic caching to the query from the 3rd to the 5th of February, and the second is from the 7th to the 10th February, and the remain query is optimized and translated into WAP script, and it's required the result data from the 5th to the 7th of February. So in this diagram, you can see that the results the query, the remain query will send to the platform WAP10, and the result from WAP10 is feedback to the semantic caching. And finally, the 3 part of the result is integrate and send back to the user. And the final part is the conclusion. This paper introduced a Think City project to evaluate urban projects. It discuss data management more precisely, time series management, and optimization via form-based semantic caching. For the future work, now we are currently implementing and validating this contribution and integrating both synthesis and real data. In the future work, we will include the heterogeneous cache management, and in addition, we will study the traditional and specific policy for traditional and semantic caching. Thank you for your listening. Now I would like to have some question about this presentation.
Thank you very much for interesting presentation. So we do have questions. So Karin Zaytoni asks, can you clarify in the architecture which query engine are you using and the way the query is translated to warp 10? So this is one question. Another one is about the use of warp 10, which is an open source. Is the company part of the project?
The first, I will answer the question about the way query is translated to the warp 10. Because in our project, we will divide the query into many kind of query. Its form will be in a specific form. So, for example, in this example, you can see that the form of query is only select the timestamp and aggregate X from area and where the T from T1 to T2. So so this form can be translated into the warp script. We'll do this function. Okay. I will how to share the other screen. Okay, I will stop the screen and share another screen to you. Okay. No. Okay. Could you see? Okay. Could you see the in the screen? In this screen, you can see that the data will select in an area, a polygon, and we'll take the data from the 10 days before. Okay, and after that we'll define a function to do this, and another function is that to do the function like this, and after that we will catch in the semantic caching and do another function. You can see in this I will answer another question. The second question.
So do you mean that you translate the query to actually this warp script with the code, like manually? Yeah, so there is no particular query engine that does this for you, from the web user interface to the final warp script?
Yeah, The first, because the query is form is in a form. So
so you mean web application form?
Yes, the form based query will have some parameter to translate to the web script, like from T1 to T2. T1 and T2 is the parameter, and the other parameter is the area A or B or C or
okay.
Okay. Okay. So that's mean that it's like a function to translate.
Yeah. Okay, thanks. And another question was about the use of Warp 10, which is an open source. Is the company part of this project?
Yeah. Actually the Warp 10 is an open source, but for more function or imply the Warp 10 in our project, we another people from the company is SendX. Is SendX will integrate the Warp 10 platform with the zero time series data or another the job with the connect with the data and the Warp 10 platform, something more and more function. The people from the SendX, the author of this paper will do this. The Daniel Florian Daniel from the SendX is is an operator of Warp 10 platform.
Okay, Karin, does this answers your questions?
Thank you for your question.
Okay, thanks. Do we have anything else to ask? Okay, looks like there is no more questions. So thank you very much for presentation. Looks like very nice project.
Thank you. Have a good day.
Thank you.
Same to you. Thanks. All right, and let us move on. Last but not least, optimal seeds discovery of traffic congestions. So Carlos Bermejo, I think, is presenting. Carlos, you are muted.
Now I will.
Yes.
Okay.
All right, we can see.
So good morning, everyone. My name is Carlos Bermejo, and I'm one of the co-authors of Optimal Seeds Discovery of Traffic Congestions. So in this talk, we will start with the table of contents. So we will introduce the motivation of our work, what we want to do that, and what they have been done. We will explain our approach, which is finding an optimal, the optimal regions in terms of traffic congestions in a city. And for that, we will split the algorithm called seed discovering in different parts. The first part is like the traffic congestion detection. The second one is the influence measurements, how we can measure the influence of the traffic congestions in the city between regions. How, which is going to be called the independent cascade model, model, sorry, and we will then optimize the problem after we define it. And due to the definition of our problem, we will have to use approximation algorithms. In this case, we will approximate the optimization problem using greedy algorithm and another algorithm, we will call it adaptive model. Then we will have an experiment with in 3 different parts. One is an evaluation of effectiveness of the algorithms versus other 3 algorithms we will design for this particular comparison. Also, with these 3 algorithms in comparison, we will evaluate the efficiency of our algorithm, and we will include a real case study with more than 10,000 traces of taxis in Shanghai. Then we will conclude our talk. So first, the motivation. Traffic congestion, as everyone knows, is a major problem in cities, and due to that it disturbs or disrupt the mobility, and for example, in public transportation, and it increases the pollutions, the CO2 emissions. The recent advances in wireless sensor networks, like IoT ecosystems, permits the development of what we call smart cities. With these sensor networks, what we can do is real-time mobility monitoring of the network, of the traffic in the city. As we can see that with this wireless sensor network, we can trace the mobility, we can get or collect mobility patterns within the city. So for that, these wireless sensor networks usually use GPS tracking and other inertial measuring units, like to measure the speed and other parameters like acceleration and so on in the vehicles. And with these mobility patterns, what we can find is abnormal situations. For example, when a traffic congestion happens. In the current related work, what they are usually doing is either using road-based models, which basically target roads in the city. They are accurate comparison with the other one, which is region-based models. But these road-based models, they are more accurate, but at a cost of computation. They need more resources for computing this. And there is another problem, which is called splitting traffic. I mean, because they are measuring road, they cannot, one particular region, I mean, in this case, one particular road can not be extrapolated to another part of the city. They are very specific. The region-based models, that is the one we will use, are more generic. They are less accurate, but they are more efficient in terms of computation. And in our approach, we call it seed discovery. What we aim with this work is trying to find the most influential regions in a city. For that, the first step is like, what is the definition of a traffic congestion for us? So the condition is of a traffic congestion happens when we lower the speed in a particular part of the city, the trips increase in time, and there is an increase in vehicular queuing. So there are more cars queuing. The first step we will do is partition the city by using the major roads. We will we will name these major roads as points, and then we will use what you can see on the right part of the slides, an approach to create more generic regions like a Voronoi diagram, but we use a Fortune's algorithm, which is very fast and efficient. The traffic congestions we will classify also not only in spatial dimension, but in temporal units. So what we can see here in the next slide on the right, if I minimize this, we can see at the bottom, we have the city split in different regions, which are the red boxes, red blocks, in this case, cubes. And every cube has a different timestamp, and which is the letter E corresponds to an event in a particular time with a particular influences. The lines you can see going from blocks to blocks are the influences that a particular region is impacting the other region. When there is a traffic in a city, it's usually traffic impacts or influence other parts of the city, in this case, other regions in our model. Oh, So for that, for knowing or trying to measure the influence of the region, we will base how a region is influenced by another region based on two things. One is the location and the time at a particular, like, that is used in previous works, and then we will add 3 correlations more, like to know that this particular region is influencing another one, or a particular region is being influenced by another one. One is the temporal, which is a traffic event A is before traffic event B, and the difference is below a threshold. We mention in the paper. Then spatial, which is based on the Euclidean distance, and then logic. What we mention here is the correlation that, for example, if you have a bridge, two bridges, one to parallel to one another, in our model, because we are collecting regions, that means, like, for example, you have traffic congestion in one part of the bridge will affect the other part, the other bridge, these kind of things. So this logic correlation will avoid these kind of situations in our model. Then how these influences spread around along the city, and in our case between regions, we will use a direct graph that nodes influence or are not non-influenced, as you can see, red as are influenced nodes, and the others are like nodes that can be influenced. And the diffusion process, we use an efficient algorithm called independent cascade model, which is, as I mentioned, computing efficient. And it has the property of submodular, which means that the longer, the greater is the network, the number of nodes in the number of regions in our case, the nodes influence and decrease. So for the definition of our problems, what we will define as JK regions is like the top J most influential regions, as we define in our paper. These JK regions problems, the independent cascade model influence influence all these regions in the city is an NP-hard problem. Therefore, that we need to use approximation algorithms. The first one is a greedy approach that is just find the best or the optimal solution at each step, and the adaptive approach, which finds the optimal region based on the previous decisions. So for example, it takes in account the previous optimal decisions, or the optimal regions in our case, to decide the next ones. And for the experiment, as I mentioned before, for the real data sets, which is we will use a data set of 10,000 taxis of Shanghai. They are collected during 2 independent months, May and August, to have like the difference between more working days and holidays. Then the total distance of these traces are 300 million kilometers. The total number of GPS coordinates is more than 400 million, and the sampling rate is 80 seconds. Every 80 seconds, the GPS or the device embedded or included in installed in the taxis in Shanghai will upload the GPS location and other parameters that we don't use in this particular study. The city of Shanghai is divided in more than 300 regions based on what I mentioned before. And for the comparison of our both approaches, the greedy and the adaptive approach, we will compare these algorithms with one which is brute force, which is an enumeration, which is optimal. It will find always the optimal number of optimal seats, therefore the optimal JK most influential regions, and max events, that maximum the number of events and most severe traffic problems, and a randomized algorithm that it will be more efficient in computing terms. As you can see in the plots, R corresponds to the number of candidate regions that we have, like, for example, 10 candidate regions, and we want to find the most influential ones, the J number of K regions as we define in our problem. So independing of the number of top influence regions, which can go from 1 to 3, the number of candidates is the same. We can see that greedy algorithms at the greedy approximation goes very close as the optimal solution, which is the enumeration problem in terms of number of influence nodes. The next part of evaluation of effectiveness, we will evaluate the adaptive algorithm comparing with the max events and randomized, and it happens similar, like, sorry, as with the greedy algorithm. It's finding, like, independently of the number of regions we want to find and keeping the candidate regions, the set we want to analyze, the find the number of K regions. It keeps the same performance. It outperforms, sorry, the max events and the randomized algorithm. The computation times, as you can imagine, for the enumeration can go like to very high numbers because it's finding always the optimal solution. Therefore, we will not compute for more than five top regions, 5 geographical regions. Sorry for these subtitles, I didn't realize. Then in the greedy algorithms, we have a prune system in the paper that I didn't mention, but basically just reduce the cost, the speed, increase the speed of the algorithm. That's what the pruning does in this for our case, and we can see that it decreases the time to compute the number of most influential regions. As we increase the number of the most influential regions, more time we need to find these optimal seeds. Then for the real case study, we have the city of Shanghai. We have like the algorithm we want to find the top 10 seats, the top 3 seats, and then in the right one is basically the Shanghai subway network, and then we can find the most influential regions based on our algorithm. For comparing, because our optimal algorithm, we don't have any ground truth. In this case, we have to find a ground truth. For that, we use a crowdsourcing service from our university that where we collect 100 respondents, we show them the map, we tell them there are 30 candidate regions and they have to score from 0 to 10. Then from all these results, we get the top 10 JK regions with an average of 73 precision. I mean, the top 10 regions. And if we compare like our optimal seats with what the crowdsourcing results that of these 100 respondents, we can have an average precision of 73. Therefore, the candidate, like the crowdsourcing is the ground truth in our case for comparisons. And as a conclusions, optimal seats, it has advantages like the low computation times, it's scalable, and it's accurate to detect the key regions that influence traffic congestions, as we can see from our last slide, the comparison with the ground truth using crowdsourcing techniques. And that's all for my talk. And any questions you have, you're welcome.
All right. Thank you very much for presentation. Do we have any questions or comments? Okay, Karin Zaytoni asks,
yes.
Do the region change over time?
The optimal seats, they change over time. Because, for example, you can imagine that you have always traffic from one part of the city to another part of the city when the people are going to work. So the optimal seats will change over time. For us, we just collect at a particular time and then we analyze the optimal seats at the particular time. The regions of the city, based on the major roads, as we split the city, they are constant in our model. But the optimal seats, they change over time due to the traffic, because if you imagine, as I mentioned in the blocks, the regions in our model, they change, they are based on time and it's a spatial temporal unit, so they change with time as well. Therefore, the algorithm will have different results with time. I hope that answers.
Yeah,
Sorry.
does this answer the question, Karin? Yes, thanks. Another question, do you put weight on the links?
The algorithm will, I mean, we don't put weights on the link. We have like this independent cascade model that tells you how these nodes or this particular region influence the other one. but we don't include any weights beforehand. There are not like this particular region is more important than this one. We don't weight that differently. I guess the links, you mean the connections, the influence between nodes, between regions in our city.
Karim? Yeah, I wonder if I can turn on mic from Karim, so maybe it's easier.
I was turning off my mic, so thank you, Carlos, for clarification.
Thank you for that.
So, okay, so I think Karin is probably satisfied with the answers. Thanks. Do we have any other comments or questions? Have you considered including some additional data sources? I would believe that spatial information about the regions could have a significant effect.
For example, for the traffic congestion, sorry, not congestion, you can have like in the parameters we have from the data sets, we can have like this, not only the speed, as I mentioned, we can have the acceleration parameters. So these kind of parameters can include like more like prediction. Like so far, like we cannot predict with like more than a few hours what is going to happen at traffic congestion, but with these other parameters, we might have better analysis of the how the traffic flows in the city with the acceleration, the braking times. We can have more like how fast they accelerate, how fast. These kind of parameters can be interesting to include in the next model.
Yeah, I was thinking that, for example, if there is residential area and then you have places with business districts, and then you have places with market districts and all these different things. So probably they also do affect how the traffic behaves. So that could also maybe help.
That's probably what the weighting can add it in the regions. Yeah, as you mentioned, in Shanghai, you can. The particular reason with the optimal seats we were finding is because the people moved from the west to the south, to the east. Sorry. There were like this traffic flow from west east for working times, and then you can see.
Yes, interesting. So any other questions or comments? No, not really. Okay, but thank you very much for your presentation.
Thank you.
All right, so looks like we've had all the presentations today, and I would like Xian to join us this conversation. So to wrap up this workshop, so it was our very first experience to go online. So hopefully you are not exhausted without the breaks, and I very liked the presentations, and I think that we've covered really different aspects of smart cities. So we were talking about data analysis, we were talking about a perspective of industries, we were talking about solutions to collect information from citizens and how this can be analyzed. So like really lots of interesting topics. And we would like now to invite everybody to feel free to open up their mics and have some sort of maybe quick wrap up or sort of discussion. For example, we have this question, in order to progress with the future versions of our workshop, because we would like to continue and have it as a nice tradition and as a nice platform to people to meet and to discuss the topics related to smart cities and urban computing and data related aspects. So what do you think are the main keywords for future research in DASC domain, what should we consider? Maybe where should we focus, or you would like to focus more? All the comments are welcome. So the stage is now open for everybody.
Yeah, everybody, you can just unmute yourself and try to share your insights.
Yes, I think one, I'm Karin. Can you hear me?
Yes, Karin, we can.
Okay.
Go ahead.
There are many things related to urban computing, smart cities, and this emergence of new technology. So I think one aspect that has been emphasized by the Finnish presenter was about the gap between the open data that will be available more and more and the applications themselves. So this data preparation, integration, heterogeneity, the volume of data, this is very, very challenging. So I think in future, this will probably raise many problems, and we are not there. We do not have solutions for dealing with all the complexity coming from different devices, different participants, different users, and also to be so maybe the trade-off between having something very generic, like open data aim to be very generic for many use cases, and the tuning some application domain to be more specific and more optimized, and so this could be interesting for the database community to tackle, I think.
So you mean how to deal with these big data challenges arising from urban computing domain? How can we deal with all this different data heterogeneity and all this
how
sort of
to make
issues?
sense from this raw data that become available but not really produced for some purpose, specific purpose. So how to fill the gap between the application needs and
Yes, thanks for sharing. Indeed, it is interesting how this open data movement goes. Like a few years ago, everybody started thinking, yes, let's go open data. But then many didn't realize how much effort it actually requires to prepare the data to be open. So the data needs maintenance as well. And the data should be very, very well documented. And all the licenses should be in place, how we can use the data, etc., and etc. And of course, if you start going and checking how different cities deal with this, so some have very well documented and established portals where from we could actually get nice open data and use it, but some are really require lots of effort to even understand what data means there. Yeah, but I think this is very relevant and interesting point. Also to involve also more database communities, because indeed they work a lot also with these issues.
So there are many other issues like standardization. We have the OGC consortium that works in this direction, and the way to make all these tools interoperate is also something.
Yeah, this is also good and nice. Also in Ella's presentation, she was talking about, for example, this 5-air platform. So it's not, as far as I remember, it's not yet standardized, right? I mean, but many like initiatives start using it. So at which point we also need to standardize different things so that we are able to use actually interoperable systems. Because of course we can't probably build the common IoT platform for all the smart cities. We should talk to each other somehow.
Was it the platform based on Open IoT? Because I didn't attend the whole workshop. Sorry, I had courses.
Yeah, so
class.
it's 5-air. I can write in chat so you could check out what is that.
It's based on NSGI, if I remember correctly.
Oh, okay.
But basically, this interoperability is for breaking the silos in different domains in the smart city. So this would, yeah, so it would be initiate many interesting applications and services for smart cities. But on the other hand, we have the privacy issues in smart cities because people want to preserve their privacy. So there's another trend that how to use, for example, machine learning algorithms to build the model without access to real data, but just the model. And so there's conflicts here, but basically we need to investigate two sides, I think.
As privacy is also a big issue when it comes to personal data, when people will share or they share their location over time, and I don't know if there were presentations in the workshop about the architecture, this combination of different paradigm like fog, clouds, and
presentation talking about the fog computing.
Yeah.
Yeah, Margaret touched this. Yes. Yeah, but indeed there were no like paper who summarized different approaches and presented different approaches like advantages or challenges. And
yes, one problem from database point of view is where to manage the data and how to optimize the global process of these distributed and heterogeneous systems. So this could be also interesting for future.
Yes, like distributed data management.
Among heterogeneous architecture or platform.
Edge computing, yes.
Edge, yes.
Yeah.
Edge, fog, and cloudlet.
Yeah, this is interesting point.
So do we have some feedback from other audience?
I'm making notes.
I think it's not so easy to motivate people to interact via Zoom. Maybe we can ask them to play music or to sing. It would be better.
last year we have the panel discussion, which was very interactive because very high senior like professors or researchers on the table, and so on the stage, and then we try to ask questions to them, and then try to initiate some discussion. So, but for this year, it's a bit weird.
Yes,
So, yeah. So we have prepared a second question regarding to the, in your mind, what are the most important or promising areas in smart industry for the future? Because in this workshop, we see different use cases like smart transportation and social networks, etc. So which, in your mind, are the most promising areas for the future smart cities?
And maybe others.
Sorry?
I don't have an answer. I mean, it's not obvious. I think in this domain, we should involve more industrial, because it's industrial and also governmental institution like cities and transportation department, and so I think this kind of workshop could be really I mean, could interest. We have seen some authors like for the presentation with WARP. I know this this system, and it's a small company in France that started this project, and it's good to have them co-author in this kind of work because they have somehow they advertise their product, and it's an open source, so they attract community maybe to get to use their framework. So the most promising maybe for me is to have this interaction between real applications, and we have real data, researchers and practitioners actually.
Under practitioners, whom do you mean here?
So all the cities have the department, the government has advanced the institution in transportation. So we are, as computer scientists, we just see the system and the data as a way to present something, but to for multidisciplinary collaboration with the researcher in transportation or engineer when it comes to transportation system, but it could be many other facilities in the city when we talk about smart cities. So to have to involve them somehow, to invite them for maybe a panel or something like this.
So you mean like municipality decision makers?
Could be municipality, yeah. Could be also some companies that are specialists in this area. So they use computer science or systems to develop real solutions. And they have sometimes they may have interesting issues to discuss with researchers.
Yes, indeed. That's true. In smart cities, we indeed need to collaborate more with actual cities. Yeah. Yes, actually, since it's online this year, we could have thought about this and invite somebody. It could be a little bit complicated to invite a person to travel a life who is not actually connected to that much to science, but something to consider.
Okay. Thank you anyway for the workshop. I'm sorry I have to leave. It's
Yeah, sure.
quite late here.
Yes, yes.
Yeah,
Thank you,
I'm
Karin,
in their
for your
side, so
thoughts. Yes.
Maybe they say some closing words and we finish it.
thank you anyway. Bye-bye.
Thank you. Bye-bye. So I don't see any comments in chat regarding the questions. So Tony Tian, thanks everybody for hard work. So maybe we also can thank you guys, everybody, for making this workshop alive. So without you, it wouldn't happen. I also would like to thank all the organizers, Xian and all other organizers of our workshop, and of course organizers of ICD and general chairs of workshops and all the support teams. So you did great job enabling this also. I also would like to thank all the participants. So I'm very happy. So we started from 60, I guess, or something like listeners. So it was very nice. And now we still have 20. So I'm very pleased that we had that wonderful participants as well. And we also had questions and comments to the presentations. I really hope that you would be interested in participating in our workshop next year, which hopefully gonna be alive, and we would be able to personally meet and discuss and have interesting panel sessions as well. So I thank you all. I give now stage to Xian.
Well, you already thanked everybody, so no. Well, thank everybody again. But I think let's hope that we can get rid of these difficult situations of this year, and we will hope that we can have face-to-face, well, better organized workshop for next year. So, of course, more interesting discussion will happen next year. So that's it from my side. Yeah.
All right. So thank guys, and I think that's it. So then we can close our workshop.
Thank you all.
Yeah. Thank you guys. Bye-bye.
Bye.